5 people were descending toward the wreck of the Titanic when contact with their submersible was lost. The wreck lies about 3,800 meters beneath the North Atlantic. Down there, the water presses against a vehicle from every direction with hundreds of times the atmospheric pressure we experience at the surface. On June 18, 2023, the submersible Titan suffered a catastrophic implosion during its descent. The accident was a modern reminder of something deep ocean engineers have understood for generations. Reaching the bottom is not simply a matter of building a machine that can sink. The machine has to survive everything the ocean does to it on the way down. And the Titanic is not even close to the deepest place humans have reached. Far below its wreck, beyond the last sunlight, beyond the depths where giant squid hunt and bioluminescent animals make their own light, the seafloor falls into the Mariana Trench. At its deepest known point, Challenger Deep, the ocean approaches 11 kilometers in depth. Humans first reached that bottom in 1960. That is the strange part of this story. We reached the deepest known point in the ocean before the first human walked on the moon. Yet more than 6 decades later, the deep sea remains one of the least directly observed environments on Earth. So how did we get there so early? And if we already reached the bottom, why do we still understand so little about what is down there? To answer that, we have to start much closer to the surface. For most of human history, entering the ocean meant holding your breath. Divers collected sponges, shellfish, pearls, and salvage from shallow coastal waters long before anyone understood the physics involved. Their bodies could tolerate a modest increase in pressure, but every additional meter made the problem harder. Water is much denser than air. As a diver descends, the pressure around the body rises quickly. Air-filled spaces become especially vulnerable. The ears and sinuses have to equalize. A person breathing compressed gas faces another set of hazards because gases behave differently as pressure changes. For early divers, the solution was not to defeat the ocean. It was simply to stay connected to the surface. Diving bells provided one of the first ways not to remain underwater without holding breath. A rigid chamber trapped a pocket of air while its occupants descended beneath the surface. Later designs could receive fresh air from above. This was a major step, but it did not solve the deepest problem. A bell could take humans down only as far as its structure, air supply, and support system allowed. Divers could walk on the bottom in heavy suits. They could recover objects, inspect wrecks, and work underwater. The true deep ocean remained inaccessible, and for a long time, no one even knew how deep it was. Before sonar, measuring the ocean floor could be startlingly simple. A ship stopped. Sailors lowered a weighted line over the side. The line continued downward until the weight touched the seabed. The length paid out gave them an estimate of the depth. It was slow. Currents could drag the line sideways. A ship could move. The bottom itself was uneven. Still, this basic method began revealing something enormous. From 1872 to 1876, the British research vessel HMS Challenger carried out what is now recognised as the first major global oceanographic expedition. Scientists aboard crossed tens of thousands of nautical miles, collecting water samples, dredging the seabed, recording temperatures, studying marine organisms, and measuring depth. In March 1875, while working in the Western Pacific near the Mariana Islands, the crew lowered a sounding line into the ocean. It kept descending. The measured depth was more than 8 kilometers. Nobody aboard could visit that bottom. They could barely imagine a machine capable of reaching it. The measurement revealed that the Pacific concealed depressions far deeper than the great mountain ranges on land are high. Later, soundings pushed estimates deeper still. Then sound changed everything. Instead of lowering a physical line all the way to the seabed, a ship could send an acoustic pulse downward and listen for its return. Measure how long the sound takes to travel to the bottom and back, account for how sound moves through seawater, and depth can be calculated. This was the beginning of a new relationship with the ocean. Humans no longer needed to touch the bottom to know that it was there. Over time, sonar would reveal trenches, ridges, plains, volcanoes, and vast structures hidden beneath kilometers of water. The ocean floor stopped being an almost featureless unknown and began becoming a landscape. But knowing the shape of that landscape was not the same as seeing it. A map could tell scientists that an abyss existed. It could not show them what was swimming through it. That required a human eye. In the 1920s, naturalist William Beebe and engineer Otis Barton began developing a machine unlike the traditional diving bells that came before it. They called it the Bathysphere. Its basic idea was brutally simple. If water pressure becomes enormous, then place the occupants inside a sphere strong enough to resist it. The Bathysphere was a thick steel ball, little more than 1.5 meters across. It did not swim. It had no engines to carry it horizontally through the deep. It was lowered from a ship on a steel cable, with Beebe and Barton sealed inside. In 1930, the Bathysphere carried Beebe and Barton hundreds of meters beneath the waters near Bermuda. Over the next several years, they pushed deeper. Then, in August 1934, they descended to more than 900 meters. At the surface, daylight filled the ocean. Down where they were now hanging, almost all of it was gone. Through the small quartz windows, Beebe described lights moving in the darkness. They were alive. Some came from animals producing their own illumination, flashes and glows in a part of the planet that sunlight could barely reach. Humans were not examining Deepsea animals dragged upward in nets. They were watching them where they actually lived. That difference mattered. But the machine had a weakness that could not be ignored. Everything depended on the cable. The cable carried the sphere downward and pulled it back toward daylight. If it failed, the bathysphere had no independent way to rise. It could not simply release ballast and return under its own buoyancy. The deeper the sphere went, the more cable had to hang beneath the ship, adding weight and increasing the engineering challenge. The bathysphere had opened a window into the deep. It had also revealed why reaching the true bottom would require a completely different machine. And the idea for that machine would come from a man who had spent years trying to travel in the opposite direction, not into the ocean. Auguste Piccard had already spent years solving a problem that seemed to have nothing to do with the ocean. He wanted to go higher. In the early 1930s, Piccard and his collaborators built pressurized gondolas that could carry people into the stratosphere beneath enormous balloons. At those altitudes, the problem was the opposite of deep-sea diving. Outside the cabin, the air pressure was extremely low. Inside, the crew needed something close to normal atmospheric conditions. The solution was a strong, sealed pressure vessel. Piccard realized that the same principle could work underwater. The environment would be reversed, but the logic was familiar. In the stratosphere, a pressure cabin holds air in against a near vacuum. In the deep ocean, a pressure cabin holds the ocean out. That insight led to the bathyscaphe. Unlike the bathysphere, a bathyscaphe did not depend on a cable to hold it from the surface. It could descend freely and return under its own buoyancy. The basic arrangement looked unusual. A heavy pressure sphere carried the crew. Above it sat a large float filled with a liquid lighter than seawater. Gasoline was used because it provided buoyancy and, unlike a tank full of air, did not dramatically shrink as the surrounding water pressure increased. To descend, the vehicle carried ballast. To rise, it released that weight. This meant the machine could sink into the deep under gravity, then become positively buoyant and climb back toward the surface without being pulled up by a ship. It solved the bathysphere's defining limitation. The deeper the vehicle went, the longer the cable no longer had to become, because there was no cable. Piccard began experimenting with the concept before the Second World War, and development continued afterward. Early bathyscaphes proved that the idea could work. Then came the vehicle that would carry the concept farther than anyone had yet gone. Trieste. Named after the city where it was developed, Trieste looked less like a modern submersible than a machine assembled from two different worlds. Its large upper float provided buoyancy. Suspended beneath it was a compact steel pressure sphere with room for two men. That sphere was the part that had to survive the full pressure of the deep ocean. That distinction explains one of the most important ideas in deep sea engineering. Pressure by itself is not always destructive. Deep sea animals survive because much of their internal chemistry and tissue is not separated from the surrounding ocean by a rigid air-filled boundary. A crude submersible is different. Its occupants need an atmosphere inside. At great depth, the water outside presses inward with enormous force, while the pressure inside remains close to what humans tolerate at the surface. The hull has to hold that difference. Every additional kilometre makes the task harder. Trieste was tested repeatedly through the 1950s. The vehicle descended thousands of metres in the Mediterranean, proving that the bathyscaphe principle was more than an elegant idea. Then the United States Navy became involved. The target was Challenger Deep. By then, sonar surveys had transformed the way scientists saw the Mariana Trench. Measurements taken by the British vessel Challenger 2 in the early 1950s helped identify the deepest known depression in the region, and the name Challenger Deep became attached to it. Modern measurements have refined the number, but the scale remains difficult to absorb. The bottom lies close to 11 kilometres below sea level. At that depth, pressure exceeds 1,000 times atmospheric pressure at the surface. A human body could never remain there inside an ordinary air-filled space. A vehicle had to become a pressure boundary strong enough to preserve a tiny pocket of surface conditions inside one of the most extreme environments on Earth. Trieste was modified for that job. The pressure sphere was strengthened. The float was enlarged. The vehicle was prepared for deeper trials in the Western Pacific. Before the final descent, the bathyscaphe had to prove that it could survive intermediate depths. Those test dives also carried its crews through the ocean's major vertical zones. Below roughly 200 meters, the twilight zone begins. Sunlight weakens rapidly. Colors vanish. Red light disappears first, then orange and yellow, until the remaining blue light becomes faint enough that vision alone is no longer reliable. For an animal living here, darkness is not simply an absence. It changes the economics of survival. Many animals solve that problem by producing their own. Bioluminescence is created through chemical reactions inside the body or through partnerships with light-producing microorganisms. It can be used to attract prey, confuse predators, communicate, hide a silhouette, or identify members of the same species. The result is one of the deep ocean's great reversals. As sunlight disappears, living light becomes more important. A submersible descending through these waters does not enter a lifeless darkness. It enters an environment where flashes, pulses, and faint glows may matter more than daylight ever did. Below about 1,000 meters, sunlight is gone. This is the bathypelagic, often called the midnight zone. The temperature is low, food arriving from above is limited. Most of it comes as marine snow, fragments of dead organisms, waste, mucus, and other organic material slowly sinking out of shallower waters. Energy is scarce. Animals adapt accordingly. The anglerfish is famous for this world, but its appearance is easy to misunderstand. Its glowing lure is not decoration. It is a hunting tool in an environment where moving too much can waste precious energy. The strange proportions of many deep-sea animals are not signs that the deep produces monsters. They are solutions. Every shape has been filtered by the same constraints: darkness, pressure, cold, and an uncertain food supply. Trieste kept going. At around 4,000 meters, the descent enters the abyssal realm. The water is permanently dark. Temperatures hover only a few degrees above freezing in many regions. The pressure has become hundreds of times greater than at the surface, yet life continues. Sea cucumbers cross the sediment. Crustaceans scavenge. Sponges and microorganisms occupy the seafloor. The abyss is not rich in energy, but it is not empty. For the people inside Trieste, the biology outside was only part of the story. The vehicle itself was under a test no previous crewed machine had completed. Metal contracted in the cold, components flexed. Seals and windows experienced forces that could not be fully reproduced by ordinary surface conditions, and below the abyss waited the hadal zone. The name comes from Hades, the underworld of Greek mythology, but the real environment needs no mythology to be extraordinary. The hadal zone occupies the deepest trenches, generally below about 6,000 meters. These trenches form where tectonic plates converge and one plate bends down beneath another. Instead of an open plain, the seafloor becomes a narrow descending valley. Pressure rises toward levels found nowhere else in the ocean. Food arriving from the surface becomes even less predictable, and yet specialized life persists. Hadal amphipods, sea cucumbers, microbes, and other organisms occupy depths that would destroy almost any human-built pressure vessel not designed specifically for them. Fish live surprisingly deep as well, although not all the way to the bottom of Challenger Deep. The deepest-known fishes appear to approach a biological limit several kilometers above the trench's deepest point. That matters. The Mariana Trench is not one uniform ecosystem from top to bottom. A creature adapted to 7,000 meters may face entirely different constraints from one living at 10,000. The deeper Trieste went, the more those distinctions mattered. By the late 1950s, the bathyscaphe had completed dives that pushed human presence deeper than ever before. The machine had proven that its basic concept worked. It could descend freely, it could survive the cold, it could release ballast and return. But none of those tests answered the final question. No crewed vehicle had yet entered Challenger Deep itself. On January 23, 1960, Jacques Piccard and US Navy Lieutenant Don Walsh climbed into Trieste. Above them was the surface of the Western Pacific. Below them was nearly 11 kilometers of ocean. The deepest descent in human history was about to begin. The weather was poor. Waves rolled across the Pacific as Trieste was prepared above Challenger Deep. The bathyscaphe was not elegant in rough water. Its enormous float made it awkward on the surface, and the crew had only a narrow window to begin the dive. At 8:23 in the morning, Jacques Piccard and Don Walsh started down. The first part of the descent was almost familiar by then. Light faded. The blue of the upper ocean weakened into grey, then black. Outside the pressure sphere, the water grew colder and the pressure climbed relentlessly. Inside, the two men remained in a tiny atmosphere close to surface conditions. That contrast was the entire mission. The ocean did not have to enter the sphere. It only had to find one weakness, a flaw in the steel, a problem in a window, a seal that could no longer hold. A structural failure at these depths would not give the crew time to repair anything. Their survival depended on the sphere continuing to resist a pressure difference that increased with every meter. Trieste dented slowly. Thousands of meters passed beneath the surface. Then came a sound. At roughly 9 kilometers down, Piccard and Walsh heard a sharp crack from somewhere in the vehicle. There was no way to stop and inspect the exterior. They were sealed inside the pressure sphere, surrounded by black water, still descending toward the deepest known point in the ocean. The sound was later traced to an outer acrylic window associated with the entrance structure, not the main pressure sphere itself. The dive continued. This moment has become one of the most dramatic details of the Trieste story, because it captures the difference between a modern engineering test and exploration at the edge of what was then possible. Below 6,000 meters, Trieste was now fully within the hadal zone. The trench walls around Challenger Deep had been created by tectonic forces operating over millions of years. Here, one oceanic plate bends beneath another, and life there has to solve problems that become increasingly severe with depth. Pressure affects proteins and cell membranes. Biological molecules must keep their shape and continue functioning while the surrounding water presses with hundreds, then more than 1,000 atmospheres. Hadal organisms use biochemical adaptations that help stabilize those systems. Some accumulate compounds that protect proteins from pressure-related disruption. Membranes are adjusted so they remain functional in cold, high-pressure conditions. These are not creatures somehow ignoring the laws of physics. Their biology works because evolution has been operating within those laws. Fish provide one particularly useful example. They can survive much deeper than humans ever could without a pressure vessel. But even fish seem to encounter a limit. Species such as the Mariana snailfish have been documented at hadal depths above 8,000 meters. They are among the deepest living vertebrates known. Yet no fish has been confirmed from the bottom of Challenger Deep itself. The reason appears to involve chemistry. As depth increases, fish require more of certain pressure-protective compounds in their tissues. At some point, the concentrations needed may interfere with normal cell function. Trieste continued downward. After nearly 5 hours, the bathyscaphe approached the sea floor. At Challenger Deep, modern measurements place the bottom at roughly 10,935 meters, with small differences depending on the survey, location, and method used. The figures reported for the 1960 dive were not identical to modern measurements. That is not surprising. Measuring the deepest point of a complex trench is not like reading a ruler placed against a wall. The seabed is uneven. Sound speed changes through the water column. Navigation and calibration matter. Later surveys improved the estimate. What mattered on January 23, 1960 was simpler. Piccard and Walsh had reached the bottom. Trieste settled onto the sediment at Challenger Deep. Above them was nearly 11 kilometers of seawater. A point on the ocean floor that had once been detected only by sounding lines and sonar now contained 2 human beings. It should have been the moment when the mystery finally opened. Instead, their view almost immediately disappeared. The bathyscaphe disturbed fine sediment as it settled. Silt rose around the vehicle and clouded the small observation window. The crew remained on the bottom for only a short time. Their famous reports included what appeared to be shrimp-like animals and an observation interpreted at the time as a flatfish. That fish became part of the mythology of the dive. A vertebrate living at the very bottom of Challenger Deep would have been remarkable. Later biological research made the observation increasingly doubtful. Confirmed fish records stop far above the deepest point of the trench. What Piccard and Walsh saw may have been another animal, perhaps a sea cucumber, or something distorted by the difficult viewing conditions. That uncertainty is more important than the old story. The first people to reach Challenger Deep had achieved one of the great exploration milestones of the 20th century, and they still could not confidently identify everything immediately outside their window. That is the central problem of deep ocean exploration. Arrival is not the same as observation. Observation is not the same as understanding. After roughly 20 minutes on the bottom, Trieste released ballast and began climbing. The ascent took several more hours. When the bathyscaphe finally returned to the surface, Piccard and Walsh had completed the first crewed journey to the deepest known part of the ocean. It seemed reasonable to assume others would soon follow. They did not. For more than half a century, no human returned to Challenger Deep. Trieste was huge, difficult to operate, and expensive to support. Its design could reach tremendous depth, but depth alone was not enough to make it an ideal research platform. The deep ocean race therefore changed after Trieste. The question was no longer simply, can a person reach the bottom? Scientists had already answered that. The harder question became, how do we study it? During the decades after 1960, deep sea science expanded in ways that were less dramatic than a single record dive, but far more important for understanding the ocean. Sonar systems improved. Submersibles became more maneuverable. Remote vehicles began returning high-quality images. Deep sea expeditions discovered hydrothermal vent ecosystem powered not directly by sunlight, but by chemical energy. Researchers documented animals adapted to pressure. Darkness, cold, and extreme food limitation. The ocean became stranger as the observations improved. And still, Challenger Deep almost untouched by people. Then in 2012, a new vehicle arrived above the Mariana Trench. It was radically different from Trieste, narrow, compact, packed with modern instruments. Its pilot was not a naval officer or an oceanographer. He was a filmmaker. James Cameron had spent years working with deep diving technology while exploring shipwrecks, including Titanic. Now he wanted to go far beyond any wreck. His vehicle, Deepsea Challenger, had been built for a solo descent to the deepest point on Earth. On March 26, 2012, Cameron began sinking through the same vertical world Piccard, and Walsh had crossed 52 years earlier. The destination had not changed. Almost everything about the way humans could observe it had. His descent was not simply a return to a record. It was a change in what reaching Challenger Deep could mean. He piloted Deepsea Challenger alone to the deepest known part of the ocean. The vehicle carried high-definition cameras, lights, sampling equipment, and systems designed to turn the dive into a scientific observation rather than a brief arrival. That distinction mattered. Trieste had proven that human beings could survive the journey. Deepsea Challenger was designed to do more once it arrived. Cameron could maneuver across the seafloor rather than simply settle into the sediment. He could record what surrounded the vehicle, examine the terrain, and collect samples for scientists to study later. The view was still narrow. Lights illuminated only a small region beyond the vehicle. Everything outside that beam remained black. Yet, compared with the 20 minutes Piccard and Walsh had spent at the bottom in 1960, this was a very different kind of access. A visit was becoming an investigation, and even that was not enough. That began happening more often in the years after Cameron's dive. New full ocean depth vehicles were built for repeated operations rather than a single historical descent. Among them was Limiting Factor, piloted by explorer Victor Vescovo during expeditions to the deep points of the world's major ocean basins. Repeated dives into hadal trenches demonstrated that full ocean depth access no longer had to be a once-in-a-generation event. That is where the idea that the ocean is unexplored becomes more complicated. We do have a global picture of the seafloor. Satellites can infer broad underwater geography by measuring subtle variations in the ocean surface caused by gravity. Ships equipped with sonar can then map selected areas in much greater detail, so the bottom is not a blank space on a map. We know where the major trenches are. We know where ridges and plains rise and fall. We know Challenger Deep is the deepest known point, but resolution changes everything. A satellite-derived map can reveal a large mountain. It cannot show every boulder on its slope. A ship using modern multi-beam sonar can produce a far more detailed map. But even that is not the same as sending cameras a few meters above the bottom. As of April 2026, about 7% of the global seafloor had been mapped using modern high-resolution systems. That is major progress. It also means most of the seafloor still has not been mapped to that standard. Direct observation is smaller by another enormous margin. NOAA notes that humans and robotic vehicles have visually observed less than 1,000% of the deep seafloor. Less than 0.001%. The deeper the environment, the harder those observations become. At Challenger Deep, almost every scientific instrument has to survive close to the maximum pressure found anywhere in the ocean. Electronics need protection. Cameras need housings and windows that resist deformation. Batteries have to operate in cold water. Sampling devices must function after descending nearly 11 kilometers and then return with their contents intact. Communication is slow and limited compared with what we expect on land. GPS signals do not penetrate kilometers of seawater. A vehicle may know the surface ship's position precisely, while still having to determine its own location through acoustic navigation and onboard instruments. And the environment being studied is immense. The hadal zone is not one trench. It is a collection of widely separated trenches and deep depressions spread across the planet. Each is shaped by its own geology, currents, chemistry, sediment supply, and connection to the waters above. Researchers have discovered that life reaches astonishing depths, but systematic comparisons across hadal environments remain difficult. Even after a surge of modern dives, the hadal zone remains one of Earth's most poorly explored habitats. That changes the meaning of the 1960 achievement. Piccard and Walsh did not finish the exploration of Challenger Deep. They crossed a threshold. Their dive answered a question that had followed humans downward for centuries. Could a crude machine survive the journey to the deepest known ocean floor? Yes, Cameron answered another. Could a smaller modern vehicle return and operate there as a scientific platform? Yes. Repeated full-depth expeditions have answered another. Can humans build machines capable of returning again and again? Yes. None of those answers means we understand the place. What we do not have is anything close to continuous observation. There is no human community watching Challenger Deep year after year. No network of cameras covers the trench. Most of its animals will never encounter the light of a submersible. Most events on the seafloor happen without anyone seeing them. That is why the deepest ocean remains unknown in a way that can sound contradictory. We have reached it, we have measured it, we have sampled it, we have photographed it, and those achievements have shown us how much observation is still missing. The story began with a modern submersible descending toward Titanic, nearly 4 kilometers down, where the ocean remains powerful enough to destroy a vehicle when its pressure boundary fails. Challenger Deep lies almost 7 kilometers farther beneath that wreck. Getting there required centuries of small advances. Breath-hold divers, bells, pressure spheres, sounding lines, sonar, bathyspheres, bathyscaphes, robotic vehicles, and finally machines capable of operating at full ocean depth. The destination once seemed impossible. Now we know humans can reach it. That was never the final problem. The deepest point on Earth is no longer unreachable. It is still largely unobserved. 5 people were descending toward the wreck of the Titanic when contact with their submersible was lost. The wreck lies about 3,800 meters beneath the North Atlantic. Down there, the water presses against a vehicle from every direction with hundreds of times the atmospheric pressure we experience at the surface. On June 18, 2023, the submersible Titan suffered a catastrophic implosion during its descent. The accident was a modern reminder of something deep ocean engineers have understood for generations. Reaching the bottom is not simply a matter of building a machine that can sink. The machine has to survive everything the ocean does to it on the way down. And the Titanic is not even close to the deepest place humans have reached. Far below its wreck, beyond the last sunlight, beyond the depths where giant squid hunt and bioluminescent animals make their own light, the seafloor falls into the Mariana Trench. At its deepest known point, Challenger Deep, The ocean approaches 11 kilometers in depth. Humans first reached that bottom in 1960. That is the strange part of this story. We reached the deepest known point in the ocean before the first human walked on the moon. Yet more than 6 decades later, the deep sea remains one of the least directly observed environments on Earth. So how did we get there so early? And if we already reached the bottom, why do we still understand so little about what is down there? To answer that, we have to start much closer to the surface. For most of human history, entering the ocean meant holding your breath. Divers collected sponges, shellfish, pearls, and salvage from shallow coastal waters long before anyone understood the physics involved. Their bodies could tolerate a modest increase in pressure, but every additional meter made the problem harder. Water is much denser than air. As a diver descends, the pressure around the body rises quickly. Air-filled spaces become especially vulnerable. The ears and sinuses have to equalize. A person breathing compressed gas faces another set of hazards because gases behave differently as pressure changes. For early divers, the solution was not to defeat the ocean. It was simply to stay connected to the surface. Diving bells provided one of the first ways not to remain underwater without holding breath. A rigid chamber trapped a pocket of air while its occupants descended beneath the surface. Later designs could receive fresh air from above. This was a major step, but it did not solve the deepest problem. A bell could take humans down only as far as its structure, air supply, and support system allowed. Divers could walk on the bottom in heavy suits. They could recover objects, inspect wrecks, and work underwater. The true deep ocean remained inaccessible, and for a long time, no one even knew how deep it was. Before sonar, measuring the ocean floor could be startlingly simple. A ship stopped. Sailors lowered a weighted line over the side. The line continued downward until the weight touched the seabed. The length paid out gave them an estimate of the depth. It was slow. Currents could drag the line sideways. A ship could move. The bottom itself was uneven. Still, this basic method began revealing something enormous. From 1872 to 1876, the British research vessel HMS Challenger carried out what is now recognised as the first major global oceanographic expedition. Scientists aboard crossed tens of thousands of nautical miles, collecting water samples, dredging the seabed, recording temperatures, studying marine organisms, and measuring depth. In March 1875, while working in the Western Pacific near the Mariana Islands, the crew lowered a sounding line into the ocean. It kept descending. The measured depth was more than 8 kilometers. Nobody aboard could visit that bottom. They could barely imagine a machine capable of reaching it. The measurement revealed that the Pacific concealed depressions far deeper than the great mountain ranges on land are high. Later, soundings pushed estimates deeper still. Then sound changed everything. Instead of lowering a physical line all the way to the seabed, a ship could send an acoustic pulse downward and listen for its return. Measure how long the sound takes to travel to the bottom and back, account for how sound moves through seawater, and depth can be calculated. This was the beginning of a new relationship with the ocean. Humans no longer needed to touch the bottom to know that it was there. Over time, sonar would reveal trenches, ridges, plains, volcanoes, and vast structures hidden beneath kilometers of water. The ocean floor stopped being an almost featureless unknown and began becoming a landscape. But knowing the shape of that landscape was not the same as seeing it. A map could tell scientists that an abyss existed. It could not show them what was swimming through it. That required a human eye. In the 1920s, naturalist William Beebe and engineer Otis Barton began developing a machine unlike the traditional diving bells that came before it. They called it the Bathysphere. Its basic idea was brutally simple. If water pressure becomes enormous, then place the occupants inside a sphere strong enough to resist it. The bathysphere was a thick steel ball little more than 1.5 meters across. It did not swim. It had no engines to carry it horizontally through the deep. It was lowered from a ship on a steel cable, with Bibby and Barton sealed inside. In 1930, the Bathysphere carried Bibby and Barton hundreds of meters beneath the waters near Bermuda. Over the next several years, they pushed deeper. Then, in August 1934, they descended to more than 900 meters. At the surface, daylight filled the ocean. Down where they were now hanging, almost all of it was gone. Through the small quartz windows, Bibby described lights moving in the darkness. They were alive. Some came from animals producing their own illumination, flashes and glows in a part of the planet that sunlight could barely reach. Humans were not examining Deepsea animals dragged upward in nets. They were watching them where they actually lived. That difference mattered. But the machine had a weakness that could not be ignored. Everything depended on the cable. The cable carried the sphere downward and pulled it back toward daylight. If it failed, the bathysphere had no independent way to rise. It could not simply release ballast and return under its own buoyancy. The deeper the sphere went, the more cable had to hang beneath the ship, adding weight and increasing the engineering challenge. The bathysphere had opened a window into the deep. It had also revealed why reaching the true bottom would require a completely different machine. And the idea for that machine would come from a man who had spent years trying to travel in the opposite direction, not into the ocean. Auguste Piccard had already spent years solving a problem that seemed to have nothing to do with the ocean. He wanted to go higher. In the early 1930s, Piccard and his collaborators built pressurized gondolas that could carry people into the stratosphere beneath enormous balloons. At those altitudes, the problem was the opposite of deep-sea diving. Outside the cabin, the air pressure was extremely low. Inside, the crew needed something close to normal atmospheric conditions. The solution was a strong, sealed pressure vessel. Piccard realized that the same principle could work underwater. The environment would be reversed, but the logic was familiar. In the stratosphere, a pressure cabin holds air in against a near vacuum. In the deep ocean, a pressure cabin holds the ocean out. That insight led to the bathyscaphe. Unlike the bathysphere, a bathyscaphe did not depend on a cable to hold it from the surface. It could descend freely and return under its own buoyancy. The basic arrangement looked unusual. A heavy pressure sphere carried the crew. Above it sat a large float filled with a liquid lighter than seawater. Gasoline was used because it provided buoyancy and, unlike a tank full of air, did not dramatically shrink as the surrounding water pressure increased. To descend, the vehicle carried ballast. To rise, it released that weight. This meant the machine could sink into the deep under gravity, then become positively buoyant and climb back toward the surface without being pulled up by a ship. It solved the bathysphere's defining limitation. The deeper the vehicle went, the longer the cable no longer had to become, because there was no cable. Piccard began experimenting with the concept before the Second World War, and development continued afterward. Early bathyscaphes proved that the idea could work. Then came the vehicle that would carry the concept farther than anyone had yet gone. Trieste. Named after the city where it was developed, Trieste looked less like a modern submersible than a machine assembled from two different worlds. Its large upper float provided buoyancy. Suspended beneath it was a compact steel pressure sphere with room for 2 men. That sphere was the part that had to survive the full pressure of the deep ocean. That distinction explains one of the most important ideas in deep-sea engineering. Pressure by itself is not always destructive. Deep-sea animals survive because much of their internal chemistry and tissue is not separated from the surrounding ocean by a rigid air-filled boundary. A crude submersible is different. Its occupants need an atmosphere inside. At great depth, the water outside presses inward with enormous force, while the pressure inside remains close to what humans tolerate at the surface. The hull has to hold that difference. Every additional kilometre makes the task harder. Trieste was tested repeatedly through the 1950s. The vehicle descended thousands of metres in the Mediterranean, proving that the bathyscaphe principle was more than an elegant idea. Then the United States Navy became involved. The target was Challenger Deep. By then, sonar surveys had transformed the way scientists saw the Mariana Trench. Measurements taken by the British vessel Challenger 2 in the early 1950s helped identify the deepest known depression in the region, and the name Challenger Deep became attached to it. Modern measurements have refined the number, but the scale remains difficult to absorb. The bottom lies close to 11 kilometres below sea level. At that depth, pressure exceeds 1,000 times atmospheric pressure at the surface. A human body could never remain there inside an ordinary air-filled space. A vehicle had to become a pressure boundary strong enough to preserve a tiny pocket of surface conditions inside one of the most extreme environments on Earth. Trieste was modified for that job. The pressure sphere was strengthened. The float was enlarged. The vehicle was prepared for deeper trials in the Western Pacific. Before the final descent, the bathyscaphe had to prove that it could survive intermediate depths. Those test dives also carried its crews through the ocean's major vertical zones. Below roughly 200 meters, the twilight zone begins. Sunlight weakens rapidly. Colors vanish. Red light disappears first, then orange and yellow, until the remaining blue light becomes faint enough that vision alone is no longer reliable. For an animal living here, darkness is not simply an absence. It changes the economics of survival. Many animals solve that problem by producing their own. Bioluminescence is created through chemical reactions inside the body or through partnerships with light-producing microorganisms. It can be used to attract prey, confuse predators, communicate, hide a silhouette, or identify members of the same species. The result is one of the deep ocean's great reversals. As sunlight disappears, living light becomes more important. A submersible descending through these waters does not enter a lifeless darkness. It enters an environment where flashes, pulses, and faint glows may matter more than daylight ever did. Below about 1,000 meters, sunlight is gone. This is the bathypelagic, often called the midnight zone. The temperature is low, food arriving from above is limited. Most of it comes as marine snow, fragments of dead organisms, waste, mucus, and other organic material slowly sinking out of shallower waters. Energy is scarce. Animals adapt accordingly. The anglerfish is famous for this world, but its appearance is easy to misunderstand. Its glowing lure is not decoration. It is a hunting tool in an environment where moving too much can waste precious energy. The strange proportions of many deep-sea animals are not signs that the deep produces monsters. They are solutions. Every shape has been filtered by the same constraints: darkness, pressure, cold, and an uncertain food supply. Trieste kept going. At around 4,000 meters, the descent enters the abyssal realm. The water is permanently dark. Temperatures hover only a few degrees above freezing in many regions. The pressure has become hundreds of times greater than at the surface, yet life continues. Sea cucumbers cross the sediment. Crustaceans scavenge. Sponges and microorganisms occupy the seafloor. The abyss is not rich in energy, but it is not empty. For the people inside Trieste, the biology outside was only part of the story. The vehicle itself was under a test no previous crewed machine had completed. Metal contracted in the cold. Components flexed. Seals and windows experienced forces that could not be fully reproduced by ordinary surface conditions, and below the abyss waited the hadal zone. The name comes from Hades, the underworld of Greek mythology, but the real environment needs no mythology to be extraordinary. The hadal zone occupies the deepest trenches, generally below about 6,000 meters. These trenches form where tectonic plates converge and one plate bends down beneath another. Instead of an open plain, the seafloor becomes a narrow descending valley. Pressure rises toward levels found nowhere else in the ocean. Food arriving from the surface becomes even less predictable, and yet specialized life persists. Hadal amphipods, sea cucumbers, microbes, and other organisms occupy depths that would destroy almost any human-built pressure vessel not designed specifically for them. Fish live surprisingly deep as well, although not all the way to the bottom of Challenger Deep. The deepest known fishes appear to approach a biological limit several kilometers above the trench's deepest point. That matters. The Mariana Trench is not one uniform ecosystem from top to bottom. A creature adapted to 7,000 meters may face entirely different constraints from one living at 10,000. The deeper Trieste went, the more those distinctions mattered. By the late 1950s, the bathyscaphe had completed dives that pushed human presence deeper than ever before. The machine had proven that its basic concept worked. It could descend freely, it could survive the cold, it could release ballast and return. But none of those tests answered the final question. No crewed vehicle had yet entered Challenger Deep itself. On January 23, 1960, Jacques Piccard and US Navy Lieutenant Don Walsh climbed into Trieste. Above them was the surface of the Western Pacific. Below them was nearly 11 kilometers of ocean. The deepest descent in human history was about to begin. The weather was poor. Waves rolled across the Pacific as Trieste was prepared above Challenger Deep. The bathyscaphe was not elegant in rough water. Its enormous float made it awkward on the surface, and the crew had only a narrow window to begin the dive. At 8:23 in the morning, Jacques Piccard and Don Walsh started down. The first part of the descent was almost familiar by then. Light faded. The blue of the upper ocean weakened into grey, then black. Outside the pressure sphere, the water grew colder and the pressure climbed relentlessly. Inside, the two men remained in a tiny atmosphere close to surface conditions. That contrast was the entire mission. The ocean did not have to enter the sphere. It only had to find one weakness, a flaw in the steel, a problem in a window, a seal that could no longer hold. A structural failure at these depths would not give the crew time to repair anything. Their survival depended on the sphere continuing to resist a pressure difference that increased with every meter. Trieste dented slowly. Thousands of meters passed beneath the surface. Then came a sound. At roughly 9 kilometers down, Piccard and Walsh heard a sharp crack from somewhere in the vehicle. There was no way to stop and inspect the exterior. They were sealed inside the pressure sphere, surrounded by black water, still descending toward the deepest known point in the ocean. The sound was later traced to an outer acrylic window associated with the entrance structure, not the main pressure sphere itself. The dive continued. This moment has become one of the most dramatic details of the Trieste story, because it captures the difference between a modern engineering test and exploration at the edge of what was then possible. Below 6,000 meters, Trieste was now fully within the hadal zone. The trench walls around Challenger Deep had been created by tectonic forces operating over millions of years. Here, one oceanic plate bends beneath another, and life there has to solve problems that become increasingly severe with depth. Pressure affects proteins and cell membranes. Biological molecules must keep their shape and continue functioning while the surrounding water presses with hundreds, then more than 1,000 atmospheres. Hadal organisms use biochemical adaptations that help stabilize those systems. Some accumulate compounds that protect proteins from pressure-related disruption. Membranes are adjusted so they remain functional in cold, high-pressure conditions. These are not creatures somehow ignoring the laws of physics. Their biology works because evolution has been operating within those laws. Fish provide one particularly useful example. They can survive much deeper than humans ever could without a pressure vessel. But even fish seem to encounter a limit. Species such as the Mariana snailfish have been documented at hadal depths above 8,000 meters. They are among the deepest living vertebrates known. Yet no fish has been confirmed from the bottom of Challenger Deep itself. The reason appears to involve chemistry. As depth increases, fish require more of certain pressure-protective compounds in their tissues. At some point, the concentrations needed may interfere with normal cell function. Trieste continued downward. After nearly 5 hours, the bathyscaphe approached the sea floor. At Challenger Deep, modern measurements place the bottom at roughly 10,935 meters, with small differences depending on the survey, location, and method used. The figures reported for the 1960 dive were not identical to modern measurements. That is not surprising. Measuring the deepest point of a complex trench is not like reading a ruler placed against a wall. The seabed is uneven. Sound speed changes through the water column. Navigation and calibration matter. Later surveys improved the estimate. What mattered on January 23, 1960 was simpler. Piccard and Walsh had reached the bottom. Trieste settled onto the sediment at Challenger Deep. Above them was nearly 11 kilometers of seawater. A point on the ocean floor that had once been detected only by sounding lines and sonar now contained 2 human beings. It should have been the moment when the mystery finally opened. Instead, their view almost immediately disappeared. The bathyscaphe disturbed fine sediment as it settled. Silt rose around the vehicle and clouded the small observation window. The crew remained on the bottom for only a short time. Their famous reports included what appeared to be shrimp-like animals and an observation interpreted at the time as a flatfish. That fish became part of the mythology of the dive. A vertebrate living at the very bottom of Challenger Deep would have been remarkable. Later biological research made the observation increasingly doubtful. Confirmed fish records stop far above the deepest point of the trench. What Piccard and Walsh saw may have been another animal, perhaps a sea cucumber, or something distorted by the difficult viewing conditions. That uncertainty is more important than the old story. The first people to reach Challenger Deep had achieved one of the great exploration milestones of the 20th century, and they still could not confidently identify everything immediately outside their window. That is the central problem of deep ocean exploration. Arrival is not the same as observation. Observation is not the same as understanding. After roughly 20 minutes on the bottom, Trieste released ballast and began climbing. The ascent took several more hours. When the bathyscaphe finally returned to the surface, Piccard and Walsh had completed the first crewed journey to the deepest known part of the ocean. It seemed reasonable to assume others would soon follow. They did not. For more than half a century, no human returned to Challenger Deep. Trieste was huge, difficult to operate, and expensive to support. Its design could reach tremendous depth, but depth alone was not enough to make it an ideal research platform. The deep ocean race therefore changed after Trieste. The question was no longer simply, can a person reach the bottom? Scientists had already answered that. The harder question became, how do we study it? During the decades after 1960, deep sea science expanded in ways that were less dramatic than a single record dive, but far more important for understanding the ocean. Sonar systems improved. Submersibles became more maneuverable. Remote vehicles began returning high-quality images. Deep sea expeditions discovered hydrothermal vent ecosystem powered not directly by sunlight, but by chemical energy. Researchers documented animals adapted to pressure. Darkness, cold, and extreme food limitation. The ocean became stranger as the observations improved. And still, Challenger Deep almost untouched by people. Then in 2012, a new vehicle arrived above the Mariana Trench. It was radically different from Trieste, narrow, compact, packed with modern instruments. Its pilot was not a naval officer or an oceanographer. He was a filmmaker. James Cameron had spent years working with deep diving technology while exploring shipwrecks, including Titanic. Now he wanted to go far beyond any wreck. His vehicle, Deepsea Challenger, had been built for a solo descent to the deepest point on Earth. On March 26, 2012, Cameron began sinking through the same vertical world Piccard, and Walsh had crossed 52 years earlier. The destination had not changed. Almost everything about the way humans could observe it had. His descent was not simply a return to a record, it was a change in what reaching Challenger Deep could mean. He piloted Deepsea Challenger alone to the deepest known part of the ocean. The vehicle carried high-definition cameras, lights, sampling equipment, and systems designed to turn the dive into a scientific observation rather than a brief arrival. That distinction mattered. Trieste had proven that human beings could survive the journey. Deepsea Challenger was designed to do more once it arrived. Cameron could maneuver across the seafloor rather than simply settle into the sediment. He could record what surrounded the vehicle, examine the terrain, and collect samples for scientists to study later. The view was still narrow. Lights illuminated only a small region beyond the vehicle. Everything outside that beam remained black. Yet, compared with the 20 minutes Piccard and Walsh had spent at the bottom in 1960, this was a very different kind of access. A visit was becoming an investigation, and even that was not enough. That began happening more often in the years after Cameron's dive. New full ocean depth vehicles were built for repeated operations rather than a single historical descent. Among them was Limiting Factor, piloted by explorer Victor Vescovo during expeditions to the deep points of the world's major ocean basins. Repeated dives into hadal trenches demonstrated that full ocean depth access no longer had to be a once-in-a-generation event. That is where the idea that the ocean is unexplored becomes more complicated. We do have a global picture of the seafloor. Satellites can infer broad underwater geography by measuring subtle variations in the ocean surface caused by gravity. Ships equipped with sonar can then map selected areas in much greater detail, so the bottom is not a blank space on a map. We know where the major trenches are. We know where ridges and plains rise and fall. We know Challenger Deep is the deepest known point, but resolution changes everything. A satellite-derived map can reveal a large mountain. It cannot show every boulder on its slope. A ship using modern multi-beam sonar can produce a far more detailed map. But even that is not the same as sending cameras a few meters above the bottom. As of April 2026, about 7% of the global seafloor had been mapped using modern high-resolution systems. That is major progress. It also means most of the seafloor still has not been mapped to that standard. Direct observation is smaller by another enormous margin. NOAA notes that humans and robotic vehicles have visually observed less than 1,000% of the deep seafloor. Less than 0.001%. The deeper the environment, the harder those observations become. At Challenger Deep, almost every scientific instrument has to survive close to the maximum pressure found anywhere in the ocean. Electronics need protection. Cameras need housings and windows that resist deformation. Batteries have to operate in cold water. Sampling devices must function after descending nearly 11 kilometers and then return with their contents intact. Communication is slow and limited compared with what we expect on land. GPS signals do not penetrate kilometers of seawater. A vehicle may know the surface ship's position precisely, while still having to determine its own location through acoustic navigation and onboard instruments. And the environment being studied is immense. The hadal zone is not one trench. It is a collection of widely separated trenches and deep depressions spread across the planet. Each is shaped by its own geology, currents, chemistry, sediment supply, and connection to the waters above. Researchers have discovered that life reaches astonishing depths, but systematic comparisons across hadal environments remain difficult. Even after a surge of modern dives, the hadal zone remains one of Earth's most poorly explored habitats. That changes the meaning of the 1960 achievement. Piccard and Walsh did not finish the exploration of Challenger Deep. They crossed a threshold. Their dive answered a question that had followed humans downward for centuries. Could a crude machine survive the journey to the deepest known ocean floor? Yes, Cameron answered another. Could a smaller modern vehicle return and operate there as a scientific platform? Yes. Repeated full-depth expeditions have answered another. Can humans build machines capable of returning again and again? Yes. None of those answers means we understand the place. What we do not have is anything close to continuous observation. There is no human community watching Challenger Deep year after year. No network of cameras covers the trench. Most of its animals will never encounter the light of a submersible. Most events on the seafloor happen without anyone seeing them. That is why the deepest ocean remains unknown in a way that can sound contradictory. We have reached it, we have measured it, we have sampled it, we have photographed it, and those achievements have shown us how much observation is still missing. The story began with a modern submersible descending toward Titanic, nearly 4 kilometers down, where the ocean remains powerful enough to destroy a vehicle when its pressure boundary fails. Challenger Deep lies almost 7 kilometers farther beneath that wreck. Getting there required centuries of small advances. Breath-hold divers, bells, pressure spheres, sounding lines, sonar, bathyspheres, bathyscaphes, robotic vehicles, and finally machines capable of operating at full ocean depth. The destination once seemed impossible. Now we know humans can reach it. That was never the final problem. The deepest point on Earth is no longer unreachable. It is still largely unobserved. 5 people were descending toward the wreck of the Titanic when contact with their submersible was lost. The wreck lies about 3,800 meters beneath the North Atlantic. Down there, the water presses against a vehicle from every direction with hundreds of times the atmospheric pressure we experience at the surface. On June 18, 2023, the submersible Titan suffered a catastrophic implosion during its descent. The accident was a modern reminder of something deep ocean engineers have understood for generations. Reaching the bottom is not simply a matter of building a machine that can sink. The machine has to survive everything the ocean does to it on the way down. And the Titanic is not even close to the deepest place humans have reached. Far below its wreck, beyond the last sunlight, beyond the depths where giant squid hunt and bioluminescent animals make their own light, the seafloor falls into the Mariana Trench. At its deepest known point, Challenger Deep, the ocean approaches 11 kilometers in depth. Humans first reached that bottom in 1960. That is the strange part of this story. We reached the deepest known point in the ocean before the first human walked on the moon. Yet more than 6 decades later, the deep sea remains one of the least directly observed environments on Earth. So how did we get there so early? And if we already reached the bottom, why do we still understand so little about what is down there? To answer that, we have to start much closer to the surface. For most of human history, entering the ocean meant holding your breath. Divers collected sponges, shellfish, pearls, and salvage from shallow coastal waters long before anyone understood the physics involved. Their bodies could tolerate a modest increase in pressure, but every additional meter made the problem harder. Water is much denser than air. As a diver descends, the pressure around the body rises quickly. air-filled spaces become especially vulnerable. The ears and sinuses have to equalize. A person breathing compressed gas faces another set of hazards because gases behave differently as pressure changes. For early divers, the solution was not to defeat the ocean. It was simply to stay connected to the surface. Diving bells provided one of the first ways not to remain underwater without holding breath. A rigid chamber trapped a pocket of air while its occupants descended beneath the surface. Later designs could receive fresh air from above. This was a major step, but it did not solve the deepest problem. A bell could take humans down only as far as its structure, air supply, and support system allowed. Divers could walk on the bottom in heavy suits. They could recover objects, inspect wrecks, and work underwater. The true deep ocean remained inaccessible, and for a long time, no one even knew how deep it was. Before sonar, measuring the ocean floor could be startlingly simple. A ship stopped. Sailors lowered a weighted line over the side. The line continued downward until the weight touched the seabed. The length paid out gave them an estimate of the depth. It was slow. Currents could drag the line sideways. A ship could move. The bottom itself was uneven. Still, this basic method began revealing something enormous. From 1872 to 1876, the British research vessel HMS Challenger carried out what is now recognised as the first major global oceanographic expedition. Scientists aboard crossed tens of thousands of nautical miles, collecting water samples, dredging the seabed, recording temperatures, studying marine organisms, and measuring depth. In March 1875, while working in the Western Pacific near the Mariana Islands, the crew lowered a sounding line into the ocean. It kept descending. The measured depth was more than 8 kilometers. Nobody aboard could visit that bottom. They could barely imagine a machine capable of reaching it. The measurement revealed that the Pacific concealed depressions far deeper than the great mountain ranges on land are high. Later, soundings pushed estimates deeper still. Then sound changed everything. Instead of lowering a physical line all the way to the seabed, a ship could send an acoustic pulse downward and listen for its return. Measure how long the sound takes to travel to the bottom and back, account for how sound moves through seawater, and depth can be calculated. This was the beginning of a new relationship with the ocean. Humans no longer needed to touch the bottom to know that it was there. Over time, sonar would reveal trenches, ridges, plains, volcanoes, and vast structures hidden beneath kilometers of water. The ocean floor stopped being an almost featureless unknown and began becoming a landscape. But knowing the shape of that landscape was not the same as seeing it. A map could tell scientists that an abyss existed. It could not show them what was swimming through it. That required a human eye. In the 1920s, naturalist William Beebe and engineer Otis Barton began developing a machine unlike the traditional diving bells that came before it. They called it the Bathysphere. Its basic idea was brutally simple. If water pressure becomes enormous, then place the occupants inside a sphere strong enough to resist it. The Bathysphere was a thick steel ball, little more than 1.5 meters across. It did not swim. It had no engines to carry it horizontally through the deep. It was lowered from a ship on a steel cable, with Beebe and Barton sealed inside. In 1930, the Bathysphere carried Beebe and Barton hundreds of meters beneath the waters near Bermuda. Over the next several years, they pushed deeper. Then, in August 1934, they descended to more than 900 meters. At the surface, daylight filled the ocean. Down where they were now hanging, almost all of it was gone. Through the small quartz windows, Beebe described lights moving in the darkness. They were alive. Some came from animals producing their own illumination, flashes and glows in a part of the planet that sunlight could barely reach. Humans were not examining Deepsea animals dragged upward in nets. They were watching them where they actually lived. That difference mattered. But the machine had a weakness that could not be ignored. Everything depended on the cable. The cable carried the sphere downward and pulled it back toward daylight. If it failed, the bathysphere had no independent way to rise. It could not simply release ballast and return under its own buoyancy. The deeper the sphere went, the more cable had to hang beneath the ship, adding weight and increasing the engineering challenge. The bathysphere had opened a window into the deep. It had also revealed why reaching the true bottom would require a completely different machine. And the idea for that machine would come from a man who had spent years trying to travel in the opposite direction, not into the ocean. Auguste Piccard had already spent years solving a problem that seemed to have nothing to do with the ocean. He wanted to go higher. In the early 1930s, Piccard and his collaborators built pressurized gondolas that could carry people into the stratosphere beneath enormous balloons. At those altitudes, the problem was the opposite of deep-sea diving. Outside the cabin, the air pressure was extremely low. Inside, the crew needed something close to normal atmospheric conditions. The solution was a strong, sealed pressure vessel. Piccard realized that the same principle could work underwater. The environment would be reversed, but the logic was familiar. In the stratosphere, a pressure cabin holds air in against a near vacuum. In the deep ocean, a pressure cabin holds the ocean out. That insight led to the bathyscaphe. Unlike the bathysphere, a bathyscaphe did not depend on a cable to hold it from the surface. It could descend freely and return under its own buoyancy. The basic arrangement looked unusual. A heavy pressure sphere carried the crew. Above it sat a large float filled with a liquid lighter than seawater. Gasoline was used because it provided buoyancy and, unlike a tank full of air, did not dramatically shrink as the surrounding water pressure increased. To descend, the vehicle carried ballast. To rise, it released that weight. This meant the machine could sink into the deep under gravity, then become positively buoyant and climb back toward the surface without being pulled up by a ship. It solved the bathysphere's defining limitation. The deeper the vehicle went, the longer the cable no longer had to become, because there was no cable. Piccard began experimenting with the concept before the Second World War, and development continued afterward. Early bathyscaphes proved that the idea could work. Then came the vehicle that would carry the concept farther than anyone had yet gone. Trieste. Named after the city where it was developed, Trieste looked less like a modern submersible than a machine assembled from two different worlds. Its large upper float provided buoyancy. Suspended beneath it was a compact steel pressure sphere with room for two men. That sphere was the part that had to survive the full pressure of the deep ocean. That distinction explains one of the most important ideas in deep-sea engineering. Pressure by itself is not always destructive. Deep-sea animals survive because much of their internal chemistry and tissue is not separated from the surrounding ocean by a rigid air-filled boundary. A crude submersible is different. Its occupants need an atmosphere inside. At great depth, the water outside presses inward with enormous force, while the pressure inside remains close to what humans tolerate at the surface. The hull has to hold that difference. Every additional kilometre makes the task harder. Trieste was tested repeatedly through the 1950s. The vehicle descended thousands of metres in the Mediterranean, proving that the bathyscaphe principle was more than an elegant idea. Then the United States Navy became involved. The target was Challenger Deep. By then, sonar surveys had transformed the way scientists saw the Mariana Trench. Measurements taken by the British vessel Challenger 2 in the early 1950s helped identify the deepest known depression in the region, and the name Challenger Deep became attached to it. Modern measurements have refined the number, but the scale remains difficult to absorb. The bottom lies close to 11 kilometres below sea level. At that depth, pressure exceeds 1,000 times atmospheric pressure at the surface. A human body could never remain there inside an ordinary air-filled space. A vehicle had to become a pressure boundary strong enough to preserve a tiny pocket of surface conditions inside one of the most extreme environments on Earth. Trieste was modified for that job. The pressure sphere was strengthened. The float was enlarged. The vehicle was prepared for deeper trials in the Western Pacific. Before the final descent, the bathyscaphe had to prove that it could survive intermediate depths. Those test dives also carried its crews through the ocean's major vertical zones. Below roughly 200 meters, the twilight zone begins. Sunlight weakens rapidly. Colors vanish. Red light disappears first, then orange and yellow, until the remaining blue light becomes faint enough that vision alone is no longer reliable. For an animal living here, darkness is not simply an absence. It changes the economics of survival. Many animals solve that problem by producing their own. Bioluminescence is created through chemical reactions inside the body or through partnerships with light-producing microorganisms. It can be used to attract prey, confuse predators, communicate, hide a silhouette, or identify members of the same species. The result is one of the deep ocean's great reversals. As sunlight disappears, living light becomes more important. A submersible descending through these waters does not enter a lifeless darkness. It enters an environment where flashes, pulses, and faint glows may matter more than daylight ever did. Below about 1,000 meters, sunlight is gone. This is the bathypelagic, often called the midnight zone. The temperature is low, food arriving from above is limited. Most of it comes as marine snow, fragments of dead organisms, waste, mucus, and other organic material slowly sinking out of shallower waters. Energy is scarce. Animals adapt accordingly. The anglerfish is famous for this world, but its appearance is easy to misunderstand. Its glowing lure is not decoration. It is a hunting tool in an environment where moving too much can waste precious energy. The strange proportions of many deep-sea animals are not signs that the deep produces monsters. They are solutions. Every shape has been filtered by the same constraints: darkness, pressure, cold, and an uncertain food supply. Trieste kept going. At around 4,000 meters, the descent enters the abyssal realm. The water is permanently dark. Temperatures hover only a few degrees above freezing in many regions. The pressure has become hundreds of times greater than at the surface, yet life continues. Sea cucumbers cross the sediment. Crustaceans scavenge. Sponges and microorganisms occupy the seafloor. The abyss is not rich in energy, but it is not empty. For the people inside Trieste, the biology outside was only part of the story. The vehicle itself was under a test no previous crewed machine had completed. Metal contracted in the cold. Components flexed. Seals and windows experienced forces that could not be fully reproduced by ordinary surface conditions, and below the abyss waited the hadal zone. The name comes from Hades, the underworld of Greek mythology, but the real environment needs no mythology to be extraordinary. The hadal zone occupies the deepest trenches, generally below about 6,000 meters. These trenches form where tectonic plates converge and one plate bends down beneath another. Instead of an open plain, the seafloor becomes a narrow descending valley. Pressure rises toward levels found nowhere else in the ocean. Food arriving from the surface becomes even less predictable, and yet specialized life persists. Hadal amphipods, sea cucumbers, microbes, and other organisms occupy depths that would destroy almost any human-built pressure vessel not designed specifically for them. Fish live surprisingly deep as well. Although not all the way to the bottom of Challenger Deep, the deepest-known fishes appear to approach a biological limit several kilometers above the trench's deepest point. That matters. The Mariana Trench is not one uniform ecosystem from top to bottom. A creature adapted to 7,000 meters may face entirely different constraints from one living at 10,000. The deeper Trieste went, the more those distinctions mattered. By the late 1950s, the bathyscaphe had completed dives that pushed human presence deeper than ever before. The machine had proven that its basic concept worked. It could descend freely, it could survive the cold, it could release ballast and return. But none of those tests answered the final question. No crewed vehicle had yet entered Challenger Deep itself. On January 23, 1960, Jacques Piccard and US Navy Lieutenant Don Walsh climbed into Trieste. Above them was the surface of the Western Pacific. Below them was nearly 11 kilometers of ocean. The deepest descent in human history was about to begin. The weather was poor. Waves rolled across the Pacific as Trieste was prepared above Challenger Deep. The bathyscaphe was not elegant in rough water. Its enormous float made it awkward on the surface, and the crew had only a narrow window to begin the dive. At 8:23 in the morning, Jacques Piccard and Don Walsh started down. The first part of the descent was almost familiar by then. Light faded, the blue of the upper ocean weakened into grey, then black. Outside the pressure sphere, the water grew colder and the pressure climbed relentlessly. Inside, the two men remained in a tiny atmosphere close to surface conditions. That contrast was the entire mission. The ocean did not have to enter the sphere, it only had to find one weakness, a flaw in the steel, a problem in a window, a seal that could no longer hold. A structural failure at these depths would not give the crew time to repair anything. Their survival depended on the sphere continuing to resist a pressure difference that increased with every meter. Trieste dented slowly. Thousands of meters passed beneath the surface. Then came a sound. At roughly 9 kilometers down, Piccard and Walsh heard a sharp crack from somewhere in the vehicle. There was no way to stop and inspect the exterior. They were sealed inside the pressure sphere, surrounded by black water, still descending toward the deepest known point in the ocean. The sound was later traced to an outer acrylic window associated with the entrance structure, not the main pressure sphere itself. The dive continued. This moment has become one of the most dramatic details of the Trieste story, because it captures the difference between a modern engineering test and exploration at the edge of what was then possible. Below 6,000 meters, Trieste was now fully within the hadal zone. The trench walls around Challenger Deep had been created by tectonic forces operating over millions of years. Here, one oceanic plate bends beneath another, and life there has to solve problems that become increasingly severe with depth. Pressure affects proteins and cell membranes. Biological molecules must keep their shape and continue functioning while the surrounding water presses with hundreds, then more than 1,000 atmospheres. Hadal organisms use biochemical adaptations that help stabilize those systems. Some accumulate compounds that protect proteins from pressure-related disruption. Membranes are adjusted so they remain functional in cold, high-pressure conditions. These are not creatures somehow ignoring the laws of physics. Their biology works because evolution has been operating within those laws. Fish provide one particularly useful example. They can survive much deeper than humans ever could without a pressure vessel. But even fish seem to encounter a limit. Species such as the Mariana snailfish have been documented at hadal depths above 8,000 meters. They are among the deepest living vertebrates known. Yet no fish has been confirmed from the bottom of Challenger Deep itself. The reason appears to involve chemistry. As depth increases, fish require more of certain pressure-protective compounds in their tissues. At some point, the concentrations needed may interfere with normal cell function. Trieste continued downward. After nearly 5 hours, the bathyscaphe approached the sea floor. At Challenger Deep, modern measurements place the bottom at roughly 10,935 meters, with small differences depending on the survey, location, and method used. The figures reported for the 1960 dive were not identical to modern measurements. That is not surprising. Measuring the deepest point of a complex trench is not like reading a ruler placed against a wall. The seabed is uneven. Sound speed changes through the water column. Navigation and calibration matter. Later surveys improved the estimate. What mattered on January 23, 1960 was simpler. Piccard and Walsh had reached the bottom. Trieste settled onto the sediment at Challenger Deep. Above them was nearly 11 kilometers of seawater. A point on the ocean floor that had once been detected only by sounding lines and sonar now contained 2 human beings. It should have been the moment when the mystery finally opened. Instead, their view almost immediately disappeared. The bathyscaphe disturbed fine sediment as it settled. Silt rose around the vehicle and clouded the small observation window. The crew remained on the bottom for only a short time. Their famous reports included what appeared to be shrimp-like animals and an observation interpreted at the time as a flatfish. That fish became part of the mythology of the dive. A vertebrate living at the very bottom of Challenger Deep would have been remarkable. Later biological research made the observation increasingly doubtful. Confirmed fish records stop far above the deepest point of the trench. What Piccard and Walsh saw may have been another animal, perhaps a sea cucumber, or something distorted by the difficult viewing conditions. That uncertainty is more important than the old story. The first people to reach Challenger Deep had achieved one of the great exploration milestones of the 20th century, and they still could not confidently identify everything immediately outside their window. That is the central problem of deep ocean exploration. Arrival is not the same as observation. Observation is not the same as understanding. After roughly 20 minutes on the bottom, Trieste released ballast and began climbing. The ascent took several more hours. When the bathyscaphe finally returned to the surface, Piccard and Walsh had completed the first crewed journey to the deepest known part of the ocean. It seemed reasonable to assume others would soon follow. They did not. For more than half a century, no human returned to Challenger Deep. Trieste was huge, difficult to operate, and expensive to support. Its design could reach tremendous depth, but depth alone was not enough to make it an ideal research platform. The deep ocean race therefore changed after Trieste. The question was no longer simply, can a person reach the bottom? Scientists had already answered that. The harder question became, how do we study it? During the decades after 1960, deep sea science expanded in ways that were less dramatic than a single record dive, but far more important for understanding the ocean. Sonar systems improved. Submersibles became more maneuverable. Remote vehicles began returning high-quality images. Deep sea expeditions discovered hydrothermal vent ecosystem powered not directly by sunlight, but by chemical energy. Researchers documented animals adapted to pressure. Darkness, cold, and extreme food limitation. The ocean became stranger as the observations improved. And still, Challenger Deep almost untouched by people. Then in 2012, a new vehicle arrived above the Mariana Trench. It was radically different from Trieste. Narrow, compact, packed with modern instruments. Its pilot was not a naval officer or an oceanographer. He was a filmmaker. James Cameron had spent years working with deep diving technology while exploring shipwrecks, including Titanic. Now he wanted to go far beyond any wreck. His vehicle, Deepsea Challenger, had been built for a solo descent to the deepest point on Earth. On March 26, 2012, Cameron began sinking through the same vertical world Piccard and Walsh had crossed 52 years earlier. The destination had not changed. Almost everything about the way humans could observe it had. His descent was not simply a return to a record. It was a change in what reaching Challenger Deep could mean. he piloted Deepsea Challenger alone to the deepest known part of the ocean. The vehicle carried high-definition cameras, lights, sampling equipment, and systems designed to turn the dive into a scientific observation rather than a brief arrival. That distinction mattered. Trieste had proven that human beings could survive the journey. Deepsea Challenger was designed to do more once it arrived. Cameron could maneuver across the seafloor rather than simply settle into the sediment. He could record what surrounded the vehicle, examine the terrain, and collect samples for scientists to study later. The view was still narrow. Lights illuminated only a small region beyond the vehicle. Everything outside that beam remained black. Yet, compared with the 20 minutes Piccard and Walsh had spent at the bottom in 1960, this was a very different kind of access. A visit was becoming an investigation, and even that was not enough. That began happening more often in the years after Cameron's dive. New full ocean depth vehicles were built for repeated operations rather than a single historical descent. Among them was Limiting Factor, piloted by explorer Victor Vescovo during expeditions to the deep points of the world's major ocean basins. Repeated dives into hadal trenches demonstrated that full ocean depth access no longer had to be a once-in-a-generation event. That is where the idea that the ocean is unexplored becomes more complicated. We do have a global picture of the seafloor. Satellites can infer broad underwater geography by measuring subtle variations in the ocean surface caused by gravity. Ships equipped with sonar can then map selected areas in much greater detail, so the bottom is not a blank space on a map. We know where the major trenches are. We know where ridges and plains rise and fall. We know Challenger Deep is the deepest known point, but resolution changes everything. A satellite-derived map can reveal a large mountain. It cannot show every boulder on its slope. A ship using modern multi-beam sonar can produce a far more detailed map. But even that is not the same as sending cameras a few meters above the bottom. As of April 2026, about 7% of the global seafloor had been mapped using modern high-resolution systems. That is major progress. It also means most of the seafloor still has not been mapped to that standard. Direct observation is smaller by another enormous margin. NOAA notes that humans and robotic vehicles have visually observed less than 1,000% of the deep seafloor. Less than 0.001%. The deeper the environment, the harder those observations become. At Challenger Deep, almost every scientific instrument has to survive close to the maximum pressure found anywhere in the ocean. Electronics need protection. Cameras need housings and windows that resist deformation. Batteries have to operate in cold water. Sampling devices must function after descending nearly 11 kilometers and then return with their contents intact. Communication is slow and limited compared with what we expect on land. GPS signals do not penetrate kilometers of seawater. A vehicle may know the surface ship's position precisely, while still having to determine its own location through acoustic navigation and onboard instruments. And the environment being studied is immense. The hadal zone is not one trench. It is a collection of widely separated trenches and deep depressions spread across the planet. Each is shaped by its own geology, currents, chemistry, sediment supply, and connection to the waters above. Researchers have discovered that life reaches astonishing depths, but systematic comparisons across hadal environments remain difficult. Even after a surge of modern dives, the hadal zone remains one of Earth's most poorly explored habitats. That changes the meaning of the 1960 achievement. Piccard and Walsh did not finish the exploration of Challenger Deep. They crossed a threshold. Their dive answered a question that had followed humans downward for centuries. Could a crude machine survive the journey to the deepest known ocean floor? Yes, Cameron answered another. Could a smaller modern vehicle return and operate there as a scientific platform? Yes. Repeated full-depth expeditions have answered another. Can humans build machines capable of returning again and again? Yes. None of those answers means we understand the place. What we do not have is anything close to continuous observation. There is no human community watching Challenger Deep year after year. No network of cameras covers the trench. Most of its animals will never encounter the light of a submersible. Most events on the seafloor happen without anyone seeing them. That is why the deepest ocean remains unknown in a way that can sound contradictory. We have reached it, we have measured it, we have sampled it, we have photographed it, and those achievements have shown us how much observation is still missing. The story began with a modern submersible descending toward Titanic, nearly 4 kilometers down, where the ocean remains powerful enough to destroy a vehicle when its pressure boundary fails. Challenger Deep lies almost 7 kilometers farther beneath that wreck. Getting there required centuries of small advances. Breath-hold divers, bells, pressure spheres, sounding lines, sonar, bathyspheres, bathyscaphes, robotic vehicles, and finally machines capable of operating at full ocean depth. The destination once seemed impossible. Now we know humans can reach it. That was never the final problem. The deepest point on Earth is no longer unreachable. It is still largely unobserved. 5 people were descending toward the wreck of the Titanic when contact with their submersible was lost. The wreck lies about 3,800 meters beneath the North Atlantic. Down there, the water presses against a vehicle from every direction with hundreds of times the atmospheric pressure we experience at the surface. On June 18, 2023, the submersible Titan suffered a catastrophic implosion during its descent. The accident was a modern reminder of something deep ocean engineers have understood for generations. Reaching the bottom is not simply a matter of building a machine that can sink. The machine has to survive everything the ocean does to it on the way down. And the Titanic is not even close to the deepest place humans have reached. Far below its wreck, beyond the last sunlight, beyond the depths where giant squid hunt and bioluminescent animals make their own light, the seafloor falls into the Mariana Trench. At its deepest known point, Challenger Deep, the ocean approaches 11 kilometers in depth. Humans first reached that bottom in 1960. That is the strange part of this story. We reached the deepest known point in the ocean before the first human walked on the moon. Yet more than 6 decades later, the deep sea remains one of the least directly observed environments on Earth. So how did we get there so early? And if we already reached the bottom, why do we still understand so little about what is down there? To answer that, we have to start much closer to the surface. For most of human history, entering the ocean meant holding your breath. Divers collected sponges, shellfish, pearls, and salvage from shallow coastal waters long before anyone understood the physics involved. Their bodies could tolerate a modest increase in pressure, but every additional meter made the problem harder. Water is much denser than air. As a diver descends, the pressure around the body rises quickly. Air-filled spaces become especially vulnerable. The ears and sinuses have to equalize. A person breathing compressed gas faces another set of hazards because gases behave differently as pressure changes. For early divers, the solution was not to defeat the ocean. It was simply to stay connected to the surface. Diving bells provided one of the first ways not to remain underwater without holding breath. A rigid chamber trapped a pocket of air while its occupants descended beneath the surface. Later designs could receive fresh air from above. This was a major step, but it did not solve the deepest problem. A bell could take humans down only as far as its structure, air supply, and support system allowed. Divers could walk on the bottom in heavy suits. They could recover objects, inspect wrecks, and work underwater. The true deep ocean remained inaccessible, and for a long time, no one even knew how deep it was. Before sonar, measuring the ocean floor could be startlingly simple. A ship stopped. sailors lowered a weighted line over the side. The line continued downward until the weight touched the seabed. The length paid out gave them an estimate of the depth. It was slow. Currents could drag the line sideways. A ship could move. The bottom itself was uneven. Still, this basic method began revealing something enormous. From 1872 to 1876, the British research vessel HMS Challenger carried out what is now recognised as the first major global oceanographic expedition. Scientists aboard crossed tens of thousands of nautical miles, collecting water samples, dredging the seabed, recording temperatures, studying marine organisms, and measuring depth. In March 1875, while working in the Western Pacific near the Mariana Islands, the crew lowered a sounding line into the ocean. It kept descending. The measured depth was more than 8 kilometers. Nobody aboard could visit that bottom. They could barely imagine a machine capable of reaching it. The measurement revealed that the Pacific concealed depressions far deeper than the great mountain ranges on land are high. Later, soundings pushed estimates deeper still. Then sound changed everything. Instead of lowering a physical line all the way to the seabed, a ship could send an acoustic pulse downward and listen for its return. Measure how long the sound takes to travel to the bottom and back, account for how sound moves through seawater, and depth can be calculated. This was the beginning of a new relationship with the ocean. Humans no longer needed to touch the bottom to know that it was there. Over time, sonar would reveal trenches, ridges, plains, volcanoes, and vast structures hidden beneath kilometers of water. The ocean floor stopped being an almost featureless unknown and began becoming a landscape. But knowing the shape of that landscape was not the same as seeing it. A map could tell scientists that an abyss existed. It could not show them what was swimming through it. That required a human eye. In the 1920s, naturalist William Beebe and engineer Otis Barton began developing a machine unlike the traditional diving bells that came before it. They called it the Bathysphere. Its basic idea was brutally simple. If water pressure becomes enormous, then place the occupants inside a sphere strong enough to resist it. The Bathysphere was a thick steel ball, little more than 1.5 meters across. It did not swim. It had no engines to carry it horizontally through the deep. It was lowered from a ship on a steel cable, with Beebe and Barton sealed inside. In 1930, the Bathysphere carried Beebe and Barton hundreds of meters beneath the waters near Bermuda. Over the next several years, they pushed deeper. Then, in August 1934, they descended to more than 900 meters. At the surface, daylight filled the ocean. Down where they were now hanging, almost all of it was gone. Through the small quartz windows, Beebe described lights moving in the darkness. They were alive. Some came from animals producing their own illumination, flashes and glows in a part of the planet that sunlight could barely reach. Humans were not examining Deepsea animals dragged upward in nets. They were watching them where they actually lived. That difference mattered. But the machine had a weakness that could not be ignored. Everything depended on the cable. The cable carried the sphere downward and pulled it back toward daylight. If it failed, the bathysphere had no independent way to rise. It could not simply release ballast and return under its own buoyancy. The deeper the sphere went, the more cable had to hang beneath the ship, adding weight and increasing the engineering challenge. The bathysphere had opened a window into the deep. It had also revealed why reaching the true bottom would require a completely different machine. And the idea for that machine would come from a man who had spent years trying to travel in the opposite direction, not into the ocean. Auguste Piccard had already spent years solving a problem that seemed to have nothing to do with the ocean. He wanted to go higher. In the early 1930s, Piccard and his collaborators built pressurized gondolas that could carry people into the stratosphere beneath enormous balloons. At those altitudes, the problem was the opposite of deep-sea diving. Outside the cabin, the air pressure was extremely low. Inside, the crew needed something close to normal atmospheric conditions. The solution was a strong, sealed pressure vessel. Piccard realized that the same principle could work underwater. The environment would be reversed, but the logic was familiar. In the stratosphere, a pressure cabin holds air in against a near vacuum. In the deep ocean, a pressure cabin holds the ocean out. That insight led to the bathyscaphe. Unlike the bathysphere, a bathyscaphe did not depend on a cable to hold it from the surface. It could descend freely and return under its own buoyancy. The basic arrangement looked unusual. A heavy pressure sphere carried the crew. Above it sat a large float filled with a liquid lighter than seawater. Gasoline was used because it provided buoyancy and, unlike a tank full of air, did not dramatically shrink as the surrounding water pressure increased. To descend, the vehicle carried ballast. To rise, it released that weight. This meant the machine could sink into the deep under gravity, then become positively buoyant and climb back toward the surface without being pulled up by a ship. It solved the bathysphere's defining limitation. The deeper the vehicle went, the longer the cable no longer had to become, because there was no cable. Piccard began experimenting with the concept before the Second World War, and development continued afterward. Early bathyscaphes proved that the idea could work. Then came the vehicle that would carry the concept farther than anyone had yet gone. Trieste. Named after the city where it was developed, Trieste looked less like a modern submersible than a machine assembled from two different worlds. Its large upper float provided buoyancy. Suspended beneath it was a compact steel pressure sphere with room for 2 men. That sphere was the part that had to survive the full pressure of the deep ocean. That distinction explains one of the most important ideas in deep sea engineering. Pressure by itself is not always destructive. Deep sea animals survive because much of their internal chemistry and tissue is not separated from the surrounding ocean by a rigid air-filled boundary. A crude submersible is different. Its occupants need an atmosphere inside. At great depth, the water outside presses inward with enormous force, while the pressure inside remains close to what humans tolerate at the surface. The hull has to hold that difference. Every additional kilometre makes the task harder. Trieste was tested repeatedly through the 1950s. The vehicle descended thousands of metres in the Mediterranean, proving that the bathyscaphe principle was more than an elegant idea. Then the United States Navy became involved. The target was Challenger Deep. By then, sonar surveys had transformed the way scientists saw the Mariana Trench. Measurements taken by the British vessel Challenger 2 in the early 1950s helped identify the deepest known depression in the region, and the name Challenger Deep became attached to it. Modern measurements have refined the number, but the scale remains difficult to absorb. The bottom lies close to 11 kilometers below sea level. At that depth, pressure exceeds 1,000 times atmospheric pressure at the surface. A human body could never remain there inside an ordinary air-filled space. A vehicle had to become a pressure boundary strong enough to preserve a tiny pocket of surface conditions inside one of the most extreme environments on Earth. Trieste was modified for that job. The pressure sphere was strengthened. The float was enlarged. The vehicle was prepared for deeper trials in the Western Pacific. Before the final descent, the bathyscaphe had to prove that it could survive intermediate depths. Those test dives also carried its crews through the ocean's major vertical zones. Below roughly 200 meters, the twilight zone begins. Sunlight weakens rapidly. Colors vanish. Red light disappears first, then orange and yellow, until the remaining blue light becomes faint enough that vision alone is no longer reliable. For an animal living here, darkness is not simply an absence. It changes the economics of survival. Many animals solve that problem by producing their own. bioluminescence is created through chemical reactions inside the body or through partnerships with light-producing microorganisms. It can be used to attract prey, confuse predators, communicate, hide a silhouette, or identify members of the same species. The result is one of the deep ocean's great reversals. As sunlight disappears, living light becomes more important. A submersible descending through these waters does not enter a lifeless darkness. It enters an environment where flashes, pulses, and faint glows may matter more than daylight ever did. Below about 1,000 meters, sunlight is gone. This is the bathypelagic, often called the midnight zone. The temperature is low, food arriving from above is limited. Most of it comes as marine snow, fragments of dead organisms, waste, mucus, and other organic material slowly sinking out of shallower waters. Energy is scarce. Animals adapt accordingly. The anglerfish is famous for this world, but its appearance is easy to misunderstand. Its glowing lure is not decoration. It is a hunting tool in an environment where moving too much can waste precious energy. The strange proportions of many deep-sea animals are not signs that the deep produces monsters. They are solutions. Every shape has been filtered by the same constraints: darkness, pressure, cold, and an uncertain food supply. Trieste kept going. At around 4,000 meters, the descent enters the abyssal realm. The water is permanently dark. Temperatures hover only a few degrees above freezing in many regions. The pressure has become hundreds of times greater than at the surface, yet life continues. Sea cucumbers cross the sediment. Crustaceans scavenge. Sponges and microorganisms occupy the seafloor. The abyss is not rich in energy, but it is not empty. For the people inside Trieste, the biology outside was only part of the story. The vehicle itself was under a test no previous crewed machine had completed. Metal contracted in the cold, components flexed. Seals and windows experienced forces that could not be fully reproduced by ordinary surface conditions, and below the abyss waited the hadal zone. The name comes from Hades, the underworld of Greek mythology, but the real environment needs no mythology to be extraordinary. The hadal zone occupies the deepest trenches, generally below about 6,000 meters. These trenches form where tectonic plates converge and one plate bends down beneath another. Instead of an open plain, the seafloor becomes a narrow descending valley. Pressure rises toward levels found nowhere else in the ocean. Food arriving from the surface becomes even less predictable, and yet specialized life persists. Hadal amphipods, sea cucumbers, microbes, and other organisms occupy depths that would destroy almost any human-built pressure vessel, not designed specifically for them. Fish live surprisingly deep as well, although not all the way to the bottom of Challenger Deep. The deepest-known fishes appear to approach a biological limit several kilometers above the trench's deepest point. That matters. The Mariana Trench is not one uniform ecosystem from top to bottom. A creature adapted to 7,000 meters may face entirely different constraints from one living at 10,000. The deeper Trieste went, the more those distinctions mattered. By the late 1950s, the bathyscaphe had completed dives that pushed human presence deeper than ever before. The machine had proven that its basic concept worked. It could descend freely, it could survive the cold, it could release ballast and return. But none of those tests answered the final question. No crewed vehicle had yet entered Challenger Deep itself. On January 23, 1960, Jacques Piccard and US Navy Lieutenant Don Walsh climbed into Trieste. Above them was the surface of the Western Pacific. Below them was nearly 11 kilometers of ocean. The deepest descent in human history was about to begin. The weather was poor. Waves rolled across the Pacific as Trieste was prepared above Challenger Deep. The bathyscaphe was not elegant in rough water. Its enormous float made it awkward on the surface, and the crew had only a narrow window to begin the dive. At 8:23 in the morning, Jacques Piccard and Don Walsh started down. The first part of the descent was almost familiar by then. Light faded, the blue of the upper ocean weakened into grey, then black. Outside the pressure sphere, the water grew colder and the pressure climbed relentlessly. Inside, the two men remained in a tiny atmosphere close to surface conditions. That contrast was the entire mission. The ocean did not have to enter the sphere, it only had to find one weakness, a flaw in the steel, a problem in a window, a seal that could no longer hold. A structural failure at these depths would not give the crew time to repair anything. Their survival depended on the sphere continuing to resist a pressure difference that increased with every metre. Trieste dented slowly. Thousands of metres passed beneath the surface. Then came a sound. At roughly 9 kilometres down, Piccard and Walsh heard a sharp crack from somewhere in the vehicle. There was no way to stop and inspect the exterior. They were sealed inside the pressure sphere, surrounded by black water, still descending toward the deepest known point in the ocean. The sound was later traced to an outer acrylic window associated with the entrance structure, not the main pressure sphere itself. The dive continued. This moment has become one of the most dramatic details of the Trieste story, because it captures the difference between a modern engineering test and exploration at the edge of what was then possible. Below 6,000 metres, Trieste was now fully within the hadal zone. The trench walls around Challenger Deep had been created by tectonic forces operating over millions of years. Here, one oceanic plate bends beneath another, and life there has to solve problems that become increasingly severe with depth. Pressure affects proteins and cell membranes. Biological molecules must keep their shape and continue functioning while the surrounding water presses with hundreds, then more than 1,000 atmospheres. Hadal organisms use biochemical adaptations that help stabilize those systems. Some accumulate compounds that protect proteins from pressure-related disruption. Membranes are adjusted so they remain functional in cold, high-pressure conditions. These are not creatures somehow ignoring the laws of physics. Their biology works because evolution has been operating within those laws. Fish provide one particularly useful example. They can survive much deeper than humans ever could without a pressure vessel. But even fish seem to encounter a limit. Species such as the Mariana snailfish have been documented at hadal depths above 8,000 metres. They are among the deepest living vertebrates known. Yet no fish has been confirmed from the bottom of Challenger Deep itself. The reason appears to involve chemistry. As depth increases, fish require more of certain pressure-protective compounds in their tissues. At some point, the concentrations needed may interfere with normal cell function. Trieste continued downward. After nearly 5 hours, the bathyscaphe approached the sea floor. At Challenger Deep, modern measurements place the bottom at roughly 10,935 metres, with small differences depending on the survey, location, and method used. The figures reported for the 1960 dive were not identical to modern measurements. That is not surprising. Measuring the deepest point of a complex trench is not like reading a ruler placed against a wall. The seabed is uneven. Sound speed changes through the water column. Navigation and calibration matter. Later surveys improved the estimate. What mattered on January 23, 1960 was simpler. Piccard and Walsh had reached the bottom. Trieste settled onto the sediment at Challenger Deep. Above them was nearly 11 kilometres of seawater. A point on the ocean floor that had once been detected only by sounding lines and sonar now contained 2 human beings. It should have been the moment when the mystery finally opened. Instead, their view almost immediately disappeared. The bathyscaphe disturbed fine sediment as it settled. Silt rose around the vehicle and clouded the small observation window. The crew remained on the bottom for only a short time. Their famous reports included what appeared to be shrimp-like animals and an observation interpreted at the time as a flatfish. That fish became part of the mythology of the dive. A vertebrate living at the very bottom of Challenger Deep would have been remarkable. Later biological research made the observation increasingly doubtful. Confirmed fish records stop far above the deepest point of the trench. What Piccard and Walsh saw may have been another animal, perhaps a sea cucumber, or something distorted by the difficult viewing conditions. That uncertainty is more important than the old story. The first people to reach Challenger Deep had achieved one of the great exploration milestones of the 20th century, and they still could not confidently identify everything immediately outside their window. That is the central problem of deep ocean exploration. Arrival is not the same as observation. Observation is not the same as understanding. After roughly 20 minutes on the bottom, Trieste released ballast and began climbing. The ascent took several more hours. When the bathyscaphe finally returned to the surface, Piccard and Walsh had completed the first crewed journey to the deepest known part of the ocean. It seemed reasonable to assume others would soon follow. They did not. For more than half a century, no human returned to Challenger Deep. Trieste was huge, difficult to operate, and expensive to support. Its design could reach tremendous depth, but depth alone was not enough to make it an ideal research platform. The deep ocean race therefore changed after Trieste. The question was no longer simply, can a person reach the bottom? Scientists had already answered that. The harder question became, how do we study it? During the decades after 1960, deep sea science expanded in ways that were less dramatic than a single record dive, but far more important for understanding the ocean. Sonar systems improved. Submersibles became more maneuverable. Remote vehicles began returning high-quality images. Deep sea expeditions discovered hydrothermal vent ecosystem powered not directly by sunlight, but by chemical energy. Researchers documented animals adapted to pressure. Darkness, cold, and extreme food limitation. The ocean became stranger as the observations improved. And still, Challenger Deep almost untouched by people. Then in 2012, a new vehicle arrived above the Mariana Trench. It was radically different from Trieste. Narrow, compact, packed with modern instruments. Its pilot was not a naval officer or an oceanographer. He was a filmmaker. James Cameron had spent years working with deep diving technology while exploring shipwrecks, including Titanic. Now he wanted to go far beyond any wreck. His vehicle, Deepsea Challenger, had been built for a solo descent to the deepest point on Earth. On March 26, 2012, Cameron began sinking through the same vertical world Piccard and Walsh had crossed 52 years earlier. The destination had not changed. Almost everything about the way humans could observe it had. His descent was not simply a return to a record. It was a change in what reaching Challenger Deep could mean. He piloted Deepsea Challenger alone to the deepest known part of the ocean. The vehicle carried high-definition cameras, lights, sampling equipment, and systems designed to turn the dive into a scientific observation rather than a brief arrival. That distinction mattered. Trieste had proven that human beings could survive the journey. Deepsea Challenger was designed to do more once it arrived. Cameron could maneuver across the seafloor rather than simply settle into the sediment. He could record what surrounded the vehicle, examine the terrain, and collect samples for scientists to study later. The view was still narrow. Lights illuminated only a small region beyond the vehicle. Everything outside that beam remained black. Yet, compared with the 20 minutes Piccard and Walsh had spent at the bottom in 1960, this was a very different kind of access. A visit was becoming an investigation, and even that was not enough. That began happening more often in the years after Cameron's dive. New full ocean depth vehicles were built for repeated operations rather than a single historical descent. Among them was limiting factor. piloted by explorer Victor Vescovo during expeditions to the deep points of the world's major ocean basins. Repeated dives into hadal trenches demonstrated that full ocean depth access no longer had to be a once-in-a-generation event. That is where the idea that the ocean is unexplored becomes more complicated. We do have a global picture of the seafloor. Satellites can infer broad underwater geography by measuring subtle variations in the ocean surface caused by gravity. Ships equipped with sonar can then map selected areas in much greater detail, so the bottom is not a blank space on a map. We know where the major trenches are. We know where ridges and plains rise and fall. We know Challenger Deep is the deepest known point, but resolution changes everything. A satellite-derived map can reveal a large mountain. It cannot show every boulder on its slope. A ship using modern multi-beam sonar can produce a far more detailed map. But even that is not the same as sending cameras a few meters above the bottom. As of April 2026, about 7% of the global seafloor had been mapped using modern high-resolution systems. That is major progress. It also means most of the seafloor still has not been mapped to that standard. Direct observation is smaller by another enormous margin. NOAA notes that humans and robotic vehicles have visually observed less than 1,000% of the deep seafloor. Less than 0.001%. The deeper the environment, the harder those observations become. At Challenger Deep, almost every scientific instrument has to survive close to the maximum pressure found anywhere in the ocean. Electronics need protection. Cameras need housings and windows that resist deformation. Batteries have to operate in cold water. Sampling devices must function after descending nearly 11 kilometers and then return with their contents intact. Communication is slow and limited compared with what we expect on land. GPS signals do not penetrate kilometers of seawater. A vehicle may know the surface ship's position precisely, while still having to determine its own location through acoustic navigation and onboard instruments. And the environment being studied is immense. The hadal zone is not one trench. It is a collection of widely separated trenches and deep depressions spread across the planet. Each is shaped by its own geology, currents, chemistry, sediment supply, and connection to the waters above. Researchers have discovered that life reaches astonishing depths, but systematic comparisons across hadal environments remain difficult. Even after a surge of modern dives, the hadal zone remains one of Earth's most poorly explored habitats. That changes the meaning of the 1960 achievement. Piccard and Walsh did not finish the exploration of Challenger Deep. They crossed a threshold. Their dive answered a question that had followed humans downward for centuries. Could a crude machine survive the journey to the deepest known ocean floor? Yes, Cameron answered another. Could a smaller modern vehicle return and operate there as a scientific platform? Yes. Repeated full-depth expeditions have answered another. Can humans build machines capable of returning again and again? Yes. None of those answers means we understand the place. What we do not have is anything close to continuous observation. There is no human community watching Challenger Deep year after year. No network of cameras covers the trench. Most of its animals will never encounter the light of a submersible. Most events on the seafloor happen without anyone seeing them. That is why the deepest ocean remains unknown in a way that can sound contradictory. We have reached it, we have measured it, we have sampled it, we have photographed it, and those achievements have shown us how much observation is still missing. The story began with a modern submersible descending toward Titanic, nearly 4 kilometers down, where the ocean remains powerful enough to destroy a vehicle when its pressure boundary fails. Challenger Deep lies almost 7 kilometers farther beneath that wreck. Getting there required centuries of small advances. Breath-hold divers, bells, pressure spheres, sounding lines, sonar, bathyspheres, bathyscaphes, robotic vehicles, and finally machines capable of operating at full ocean depth. The destination once seemed impossible. Now we know humans can reach it. That was never the final problem. The deepest point on Earth is no longer unreachable. It is still largely unobserved. 5 people were descending toward the wreck of the Titanic when contact with their submersible was lost. The wreck lies about 3,800 meters beneath the North Atlantic. Down there, the water presses against a vehicle from every direction with hundreds of times the atmospheric pressure we experience at the surface. On June 18, 2023, the submersible Titan suffered a catastrophic implosion during its descent. The accident was a modern reminder of something deep ocean engineers have understood for generations. Reaching the bottom is not simply a matter of building a machine that can sink. The machine has to survive everything the ocean does to it on the way down. And the Titanic is not even close to the deepest place humans have reached. Far below its wreck, beyond the last sunlight, beyond the depths where giant squid hunt and bioluminescent animals make their own light, the seafloor falls into the Mariana Trench. At its deepest known point, Challenger Deep, the ocean approaches 11 kilometers in depth. Humans first reached that bottom in 1960. That is the strange part of this story. We reached the deepest known point in the ocean before the first human walked on the moon. Yet more than 6 decades later, the deep sea remains one of the least directly observed environments on Earth. So how did we get there so early? And if we already reached the bottom, why do we still understand so little about what is down there? To answer that, we have to start much closer to the surface. For most of human history, entering the ocean meant holding your breath. Divers collected sponges, shellfish, pearls, and salvage from shallow coastal waters long before anyone understood the physics involved. Their bodies could tolerate a modest increase in pressure, but every additional meter made the problem harder. Water is much denser than air. As a diver descends, the pressure around the body rises quickly. Air-filled spaces become especially vulnerable. The ears and sinuses have to equalize. A person breathing compressed gas faces another set of hazards because gases behave differently as pressure changes. For early divers, the solution was not to defeat the ocean. It was simply to stay connected to the surface. Diving bells provided one of the first ways not to remain underwater without holding breath. A rigid chamber trapped a pocket of air while its occupants descended beneath the surface. Later designs could receive fresh air from above. This was a major step, but it did not solve the deepest problem. A bell could take humans down only as far as its structure, air supply, and support system allowed. Divers could walk on the bottom in heavy suits. They could recover objects, inspect wrecks, and work underwater. The true deep ocean remained inaccessible, and for a long time, no one even knew how deep it was. Before sonar, measuring the ocean floor could be startlingly simple. A ship stopped. Sailors lowered a weighted line over the side. The line continued downward until the weight touched the seabed. The length paid out gave them an estimate of the depth. It was slow. Currents could drag the line sideways. A ship could move. The bottom itself was uneven. Still, this basic method began revealing something enormous. From 1872 to 1876, the British research vessel HMS Challenger carried out what is now recognised as the first major global oceanographic expedition. Scientists aboard crossed tens of thousands of nautical miles, collecting water samples, dredging the seabed, recording temperatures, studying marine organisms, and measuring depth. In March 1875, while working in the Western Pacific near the Mariana Islands, the crew lowered a sounding line into the ocean. It kept descending. The measured depth was more than 8 kilometers. Nobody aboard could visit that bottom. They could barely imagine a machine capable of reaching it. The measurement revealed that the Pacific concealed depressions far deeper than the great mountain ranges on land are high. Later, soundings pushed estimates deeper still. Then sound changed everything. Instead of lowering a physical line all the way to the seabed, a ship could send an acoustic pulse downward and listen for its return. Measure how long the sound takes to travel to the bottom and back, account for how sound moves through seawater, and depth can be calculated. This was the beginning of a new relationship with the ocean. Humans no longer needed to touch the bottom to know that it was there. Over time, sonar would reveal trenches, ridges, plains, volcanoes, and vast structures hidden beneath kilometers of water. The ocean floor stopped being an almost featureless unknown and began becoming a landscape. But knowing the shape of that landscape was not the same as seeing it. A map could tell scientists that an abyss existed. It could not show them what was swimming through it. That required a human eye. In the 1920s, naturalist William Beebe and engineer Otis Barton began developing a machine unlike the traditional diving bells that came before it. They called it the Bathysphere. Its basic idea was brutally simple. If water pressure becomes enormous, then place the occupants inside a sphere strong enough to resist it. The Bathysphere was a thick steel ball, little more than 1.5 meters across. It did not swim. It had no engines to carry it horizontally through the deep. It was lowered from a ship on a steel cable, with Beebe and Barton sealed inside. In 1930, the Bathysphere carried Beebe and Barton hundreds of meters beneath the waters near Bermuda. Over the next several years, they pushed deeper. Then, in August 1934, they descended to more than 900 meters. At the surface, daylight filled the ocean. Down where they were now hanging, almost all of it was gone. Through the small quartz windows, Beebe described lights moving in the darkness. They were alive. Some came from animals producing their own illumination, flashes and glows in a part of the planet that sunlight could barely reach. Humans were not examining Deepsea animals dragged upward in nets. They were watching them where they actually lived. That difference mattered. But the machine had a weakness that could not be ignored. Everything depended on the cable. The cable carried the sphere downward and pulled it back toward daylight. If it failed, the bathysphere had no independent way to rise. It could not simply release ballast and return under its own buoyancy. The deeper the sphere went, the more cable had to hang beneath the ship, adding weight and increasing the engineering challenge. The bathysphere had opened a window into the deep. It had also revealed why reaching the true bottom would require a completely different machine. And the idea for that machine would come from a man who had spent years trying to travel in the opposite direction, not into the ocean. Auguste Piccard had already spent years solving a problem that seemed to have nothing to do with the ocean. He wanted to go higher. In the early 1930s, Piccard and his collaborators built pressurized gondolas that could carry people into the stratosphere beneath enormous balloons. At those altitudes, the problem was the opposite of deep-sea diving. Outside the cabin, the air pressure was extremely low. Inside, the crew needed something close to normal atmospheric conditions. The solution was a strong, sealed pressure vessel. Piccard realized that the same principle could work underwater. The environment would be reversed, but the logic was familiar. In the stratosphere, a pressure cabin holds air in against a near vacuum. In the deep ocean, a pressure cabin holds the ocean out. That insight led to the bathyscaphe. Unlike the bathysphere, a bathyscaphe did not depend on a cable to hold it from the surface. It could descend freely and return under its own buoyancy. The basic arrangement looked unusual. A heavy pressure sphere carried the crew. Above it sat a large float filled with a liquid lighter than seawater. Gasoline was used because it provided buoyancy and, unlike a tank full of air, did not dramatically shrink as the surrounding water pressure increased. To descend, the vehicle carried ballast. To rise, It released that weight. This meant the machine could sink into the deep under gravity, then become positively buoyant and climb back toward the surface without being pulled up by a ship. It solved the bathysphere's defining limitation. The deeper the vehicle went, the longer the cable no longer had to become, because there was no cable. Piccard began experimenting with the concept before the Second World War, and development continued afterward. Early bathyscaphes proved that the idea could work. Then came the vehicle that would carry the concept farther than anyone had yet gone. Trieste. Named after the city where it was developed, Trieste looked less like a modern submersible than a machine assembled from two different worlds. Its large upper float provided buoyancy. Suspended beneath it was a compact steel pressure sphere with room for 2 men. That sphere was the part that had to survive the full pressure of the deep ocean. That distinction explains one of the most important ideas in deep sea engineering. Pressure by itself is not always destructive. Deep sea animals survive because much of their internal chemistry and tissue is not separated from the surrounding ocean by a rigid air-filled boundary. A crude submersible is different. Its occupants need an atmosphere inside. At great depth, the water outside presses inward with enormous force, while the pressure inside remains close to what humans tolerate at the surface. The hull has to hold that difference. Every additional kilometre makes the task harder. Trieste was tested repeatedly through the 1950s. The vehicle descended thousands of metres in the Mediterranean, proving that the bathyscaphe principle was more than an elegant idea. Then the United States Navy became involved. The target was Challenger Deep. By then, sonar surveys had transformed the way scientists saw the Mariana Trench. Measurements taken by the British vessel Challenger 2 in the early 1950s helped identify the deepest known depression in the region, and the name Challenger Deep became attached to it. Modern measurements have refined the number, but the scale remains difficult to absorb. The bottom lies close to 11 kilometres below sea level. At that depth, pressure exceeds 1,000 times atmospheric pressure at the surface. A human body could never remain there inside an ordinary air-filled space. A vehicle had to become a pressure boundary strong enough to preserve a tiny pocket of surface conditions inside one of the most extreme environments on Earth. Trieste was modified for that job. The pressure sphere was strengthened. The float was enlarged. The vehicle was prepared for deeper trials in the Western Pacific. Before the final descent, the bathyscaphe had to prove that it could survive intermediate depths. Those test dives also carried its crews through the ocean's major vertical zones. Below roughly 200 meters, the twilight zone begins. Sunlight weakens rapidly. Colors vanish. Red light disappears first, then orange and yellow, until the remaining blue light becomes faint enough that vision alone is no longer reliable. For an animal living here, darkness is not simply an absence. It changes the economics of survival. Many animals solve that problem by producing their own. Bioluminescence is created through chemical reactions inside the body or through partnerships with light-producing microorganisms. It can be used to attract prey, confuse predators, communicate, hide a silhouette, or identify members of the same species. The result is one of the deep ocean's great reversals. As sunlight disappears, living light becomes more important. A submersible descending through these waters does not enter a lifeless darkness. It enters an environment where flashes, pulses, and faint glows may matter more than daylight ever did. Below about 1,000 meters, sunlight is gone. This is the bathypelagic, often called the midnight zone. The temperature is low, food arriving from above is limited. Most of it comes as marine snow, fragments of dead organisms, waste, mucus, and other organic material slowly sinking out of shallower waters. Energy is scarce. Animals adapt accordingly. The anglerfish is famous for this world, but its appearance is easy to misunderstand. Its glowing lure is not decoration. It is a hunting tool in an environment where moving too much can waste precious energy. The strange proportions of many deep-sea animals are not signs that the deep produces monsters. They are solutions. Every shape has been filtered by the same constraints: darkness, pressure, cold, and an uncertain food supply. Trieste kept going. At around 4,000 meters, the descent enters the abyssal realm. The water is permanently dark. Temperatures hover only a few degrees above freezing in many regions. The pressure has become hundreds of times greater than at the surface, yet life continues. Sea cucumbers cross the sediment. Crustaceans scavenge. Sponges and microorganisms occupy the seafloor. The abyss is not rich in energy, but it is not empty. For the people inside Trieste, the biology outside was only part of the story. The vehicle itself was under a test no previous crewed machine had completed. Metal contracted in the cold. Components flexed. Seals and windows experienced forces that could not be fully reproduced by ordinary surface conditions, and below the abyss waited the hadal zone. The name comes from Hades, the underworld of Greek mythology, but the real environment needs no mythology to be extraordinary. The hadal zone occupies the deepest trenches, generally below about 6,000 meters. These trenches form where tectonic plates converge and one plate bends down beneath another. Instead of an open plain, the seafloor becomes a narrow descending valley. Pressure rises toward levels found nowhere else in the ocean. Food arriving from the surface becomes even less predictable, and yet specialized life persists. Hadal amphipods, sea cucumbers, microbes, and other organisms occupy depths that would destroy almost any human-built pressure vessel not designed specifically for them. Fish live surprisingly deep as well. Although not all the way to the bottom of Challenger Deep, the deepest known fishes appear to approach a biological limit several kilometers above the trench's deepest point. That matters. The Mariana Trench is not one uniform ecosystem from top to bottom. A creature adapted to 7,000 meters may face entirely different constraints from one living at 10,000. The deeper Trieste went, the more those distinctions mattered. By the late 1950s, the bathyscaphe had completed dives that pushed human presence deeper than ever before. The machine had proven that its basic concept worked. It could descend freely, it could survive the cold, it could release ballast and return. But none of those tests answered the final question. No crewed vehicle had yet entered Challenger Deep itself. On January 23, 1960, Jacques Piccard and US Navy Lieutenant Don Walsh climbed into Trieste. Above them was the surface of the Western Pacific. Below them was nearly 11 kilometers of ocean. The deepest descent in human history was about to begin. The weather was poor. Waves rolled across the Pacific as Trieste was prepared above Challenger Deep. The bathyscaphe was not elegant in rough water. Its enormous float made it awkward on the surface, and the crew had only a narrow window to begin the dive. At 8:23 in the morning, Jacques Piccard and Don Walsh started down. The first part of the descent was almost familiar by then. Light faded. The blue of the upper ocean weakened into grey, then black. Outside the pressure sphere, the water grew colder and the pressure climbed relentlessly. Inside, the two men remained in a tiny atmosphere close to surface conditions. That contrast was the entire mission. The ocean did not have to enter the sphere. It only had to find one weakness, a flaw in the steel, a problem in a window, a seal that could no longer hold. A structural failure at these depths would not give the crew time to repair anything. Their survival depended on the sphere continuing to resist a pressure difference that increased with every meter. Trieste dented slowly. Thousands of meters passed beneath the surface. Then came a sound. At roughly 9 kilometers down, Piccard and Walsh heard a sharp crack from somewhere in the vehicle. There was no way to stop and inspect the exterior. They were sealed inside the pressure sphere, surrounded by black water, still descending toward the deepest known point in the ocean. The sound was later traced to an outer acrylic window associated with the entrance structure, not the main pressure sphere itself. The dive continued. This moment has become one of the most dramatic details of the Trieste story because it captures the difference between a modern engineering test and exploration at the edge of what was then possible. Below 6,000 meters, Trieste was now fully within the hadal zone. The trench walls around Challenger Deep had been created by tectonic forces operating over millions of years. Here, one oceanic plate bends beneath another, and life there has to solve problems that become increasingly severe with depth. Pressure affects proteins and cell membranes. Biological molecules must keep their shape and continue functioning while the surrounding water presses with hundreds, then more than 1,000 atmospheres. Hadal organisms use biochemical adaptations that help stabilize those systems. Some accumulate compounds that protect proteins from pressure-related disruption. Membranes are adjusted so they remain functional in cold, high-pressure conditions. These are not creatures somehow ignoring the laws of physics. Their biology works because evolution has been operating within those laws. Fish provide one particularly useful example. They can survive much deeper than humans ever could without a pressure vessel. But even fish seem to encounter a limit. Species such as the Mariana snailfish have been documented at hadal depths above 8,000 meters. They are among the deepest living vertebrates known. Yet no fish has been confirmed from the bottom of Challenger Deep itself. The reason appears to involve chemistry. As depth increases, fish require more of certain pressure-protective compounds in their tissues. At some point, the concentrations needed may interfere with normal cell function. Trieste continued downward. After nearly 5 hours, the bathyscaphe approached the sea floor. At Challenger Deep, modern measurements place the bottom at roughly 10,935 meters, with small differences depending on the survey, location, and method used. The figures reported for the 1960 dive were not identical to modern measurements. That is not surprising. Measuring the deepest point of a complex trench is not like reading a ruler placed against a wall. The seabed is uneven. Sound speed changes through the water column. Navigation and calibration matter. Later surveys improved the estimate. What mattered on January 23, 1960 was simpler. Piccard and Walsh had reached the bottom. Trieste settled onto the sediment at Challenger Deep. Above them was nearly 11 kilometers of seawater. A point on the ocean floor that had once been detected only by sounding lines and sonar now contained 2 human beings. It should have been the moment when the mystery finally opened. Instead, their view almost immediately disappeared. The bathyscaphe disturbed fine sediment as it settled. Silt rose around the vehicle and clouded the small observation window. The crew remained on the bottom for only a short time. Their famous reports included what appeared to be shrimp-like animals and an observation interpreted at the time as a flatfish. That fish became part of the mythology of the dive. A vertebrate living at the very bottom of Challenger Deep would have been remarkable. Later biological research made the observation increasingly doubtful. Confirmed fish records stop far above the deepest point of the trench. What Piccard and Walsh saw may have been another animal, perhaps a sea cucumber, or something distorted by the difficult viewing conditions. That uncertainty is more important than the old story. The first people to reach Challenger Deep had achieved one of the great exploration milestones of the 20th century, and they still could not confidently identify everything immediately outside their window. That is the central problem of deep ocean exploration. Arrival is not the same as observation. Observation is not the same as understanding. After roughly 20 minutes on the bottom, Trieste released ballast and began climbing. The ascent took several more hours. When the bathyscaphe finally returned to the surface, Piccard and Walsh had completed the first crewed journey to the deepest known part of the ocean. It seemed reasonable to assume others would soon follow. They did not. For more than half a century, no human returned to Challenger Deep. Trieste was huge, difficult to operate, and expensive to support. Its design could reach tremendous depth, but depth alone was not enough to make it an ideal research platform. The deep ocean race therefore changed after Trieste. The question was no longer simply, can a person reach the bottom? Scientists had already answered that. The harder question became, how do we study it? During the decades after 1960, deep sea science expanded in ways that were less dramatic than a single record dive, but far more important for understanding the ocean. Sonar systems improved. Submersibles became more maneuverable. Remote vehicles began returning high-quality images. Deep sea expeditions discovered hydrothermal vent ecosystem powered not directly by sunlight, but by chemical energy. Researchers documented animals adapted to pressure. Darkness, cold, and extreme food limitation. The ocean became stranger as the observed changes improved. And still, Challenger Deep almost untouched by people. Then in 2012, a new vehicle arrived above the Mariana Trench. It was radically different from Trieste. Narrow, compact, packed with modern instruments. Its pilot was not a naval officer or an oceanographer. He was a filmmaker. James Cameron had spent years working with deep diving technology while exploring shipwrecks, including Titanic. Now he wanted to go far beyond any wreck. His vehicle, Deepsea Challenger, had been built for a solo descent to the deepest point on Earth. On March 26, 2012, Cameron began sinking through the same vertical world Piccard, and Walsh had crossed 52 years earlier. The destination had not changed. Almost everything about the way humans could observe it had. His descent was not simply a return to a record. It was a change in what reaching Challenger Deep could mean. He piloted Deepsea Challenger alone to the deepest known part of the ocean. The vehicle carried high-definition cameras, lights, sampling equipment, and systems designed to turn the dive into a scientific observation rather than a brief arrival. That distinction mattered. Trieste had proven that human beings could survive the journey. Deepsea Challenger was designed to do more once it arrived. Cameron could maneuver across the seafloor rather than simply settle into the sediment. He could record what surrounded the vehicle, examine the terrain, and collect samples for scientists to study later. The view was still narrow. Lights illuminated only a small region beyond the vehicle. Everything outside that beam remained black. Yet, compared with the 20 minutes Piccard and Walsh had spent at the bottom in 1960, this was a very different kind of access. A visit was becoming an investigation, and even that was not enough. That began happening more often in the years after Cameron's dive. New full ocean depth vehicles were built for repeated operations rather than a single historical descent. Among them was Limiting Factor, piloted by explorer Victor Vescovo during expeditions to the deep points of the world's major ocean basins. Repeated dives into hadal trenches demonstrated that full ocean depth access no longer had to be a once-in-a-generation event. That is where the idea that the ocean is unexplored becomes more complicated. We do have a global picture of the seafloor. Satellites can infer broad underwater geography by measuring subtle variations in the ocean surface caused by gravity. Ships equipped with sonar can then map selected areas in much greater detail, so the bottom is not a blank space on a map. We know where the major trenches are. We know where ridges and plains rise and fall. We know Challenger Deep is the deepest known point, but resolution changes everything. A satellite-derived map can reveal a large mountain. It cannot show every boulder on its slope. A ship using modern multi-beam sonar can produce a far more detailed map. But even that is not the same as sending cameras a few meters above the bottom. As of April 2026, about 28, 7% of the global seafloor had been mapped using modern high-resolution systems. That is major progress. It also means most of the seafloor still has not been mapped to that standard. Direct observation is smaller by another enormous margin. NOAA notes that humans and robotic vehicles have visually observed less than 1,000% of the deep seafloor. Less than 0.001%. The deeper the environment, the harder those observations become. At Challenger Deep, almost every scientific instrument has to survive close to the maximum pressure found anywhere in the ocean. Electronics need protection. Cameras need housings and windows that resist deformation. Batteries have to operate in cold water. Sampling devices must function after descending nearly 11 kilometers and then return with their contents intact. Communication is slow and limited compared with what we expect on land. GPS signals do not penetrate kilometers of seawater. A vehicle may know the surface ship's position precisely, while still having to determine its own location through acoustic navigation and onboard instruments. And the environment being studied is immense. The hadal zone is not one trench. It is a collection of widely separated trenches and deep depressions spread across the planet. Each is shaped by its own geology, currents, chemistry, sediment supply, and connection to the waters above. Researchers have discovered that life reaches astonishing depths, but systematic comparisons across hadal environments remain difficult. Even after a surge of modern dives, the hadal zone remains one of Earth's most poorly explored habitats. That changes the meaning of the 1960 achievement. Piccard and Walsh did not finish the exploration of Challenger Deep. They crossed a threshold. Their dive answered a question that had followed humans downward for centuries. Could a crude machine survive the journey to the deepest known ocean floor? Yes, Cameron answered another. Could a smaller modern vehicle return and operate there as a scientific platform? Yes. Repeated full-depth expeditions have answered another. Can humans build machines capable of returning again and again? Yes. None of those answers means we understand the place. What we do not have is anything close to continuous observation. There is no human community watching Challenger Deep year after year. No network of cameras covers the trench. Most of its animals will never encounter the light of a submersible. Most events on the seafloor happen without anyone seeing them. That is why the deepest ocean remains unknown in a way that can sound contradictory. We have reached it, we have measured it, we have sampled it, we have photographed it, and those achievements have shown us how much observation is still missing. The story began with a modern submersible descending toward Titanic, nearly 4 kilometers down, where the ocean remains powerful enough to destroy a vehicle when its pressure boundary fails. Challenger Deep lies almost 7 kilometers farther beneath that wreck. Getting there required centuries of small advances. Breath-hold divers, bells, pressure spheres, sounding lines, sonar, bathyspheres, bathyscaphes, robotic vehicles, and finally machines capable of operating at full ocean depth. The destination once seemed impossible. Now we know humans can reach it. That was never the final problem. The deepest point on Earth is no longer unreachable. It is still largely unobserved.